All right, let's all gather in the center of the room. In 2 minutes or so, we'll get started with the afternoon session. Okay. As people stream in, I'd like to welcome everybody to the afternoon session of the first day of real-world cryptography. This session will be focused on secure communications, and there's some great talks coming up. So first, let's see, the doors are close to closed. I hear quiet going over the room. All right, we're all ready. Okay, so first I'd like to it's my pleasure to welcome Nadim Kobesi, who's going to talk about Noise Explorer. Nadim?
Hello? Is this on? Can you hear me? La 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 la, la la la. Okay, great, awesome. Well, thank you very much for being here, and thank you for giving me this great opportunity to talk about my research, which I really care about and I really hope is useful to you all. So thank you. Thank you very much. This is joint work with my thesis advisor, Kartik Bhargavan, who is here in the audience, potentially against his will. No one knows. We'll find out. It's called Noise Explorer, the fully automated modeling, analysis, and verification for arbitrary noise protocols. So noise protocols, that's a bit misleading. When you first hear that, you'll think there are protocols called noise protocol, but that's not necessarily true, because noise is actually a protocol framework, which is a framework for secure channel protocols, not disk encryption protocols or anything like that. So noise is actually a framework for designing crypto protocols. They're based on Diffie-Hellman key agreement. They kind of maybe look a little bit like something like TLS, like any other secure channel system, but they're not TLS. And the most interesting part of noise is actually the fact that the framework, the noise protocol framework, has a simple language for describing the messages within the noise protocol. And from that language, which looks, by the way, something like that, see on the right. So that's a full noise handshake pattern, which is essentially a noise protocol. From that description, you have the complex state transformations, which are specified in the noise specification. They essentially say, well, this token's here, we're going to have that transcript hash mixed in, and so on. So all of these rules contained in the noise spec kick in, and then you get a whole secure channel protocol thing, which is really cool. Now, the author of noise is Trevor Perrin. This is Trevor Perrin. And he gave an excellent talk about noise last year here at Real World Crypto 2018. It was held in Zurich. So please check out his talk. He created noise. I did not make noise. Except for now, I'm certainly making a lot of noise. Thanks, Ben. That was a great joke. My friend Ben told me this joke. And so, yeah, it's on YouTube, and the link is on the screen, and it's no longer on. OK, all right. So let's try to understand the notation of noise. So you have this thing on the right, which says IK. And if I can, OK. So this is like the name of it. And then you have these tokens. So if you have an arrow going from left to right, it means that the initiator, or Alice, is sending a message to Bob, the responder. If you have an arrow going from right to left, it means that the responder, Bob, is replying to the initiator, Alice. And when you have these ellipses, 3 dots, it means that whatever happened before actually happened before the session started and people started talking and the protocol was live. So if you have this thing here, like an S token, this is like before the protocol started, Bob sent his long-term static pre-key, maybe, for example, to Alice. And when the protocol started, Alice sent a public ephemeral key to Bob. And she also did, for example, a Diffie-Hellman shared secret derivation using her private ephemeral key and Bob's public static key, and so on and so forth. And so every one of these arrows, especially only after the ellipses, actually also could contain a payload, and which is like a message, a photo, whatever. And these payloads are opportunistically encrypted as well. So once we have shared secret agreement, encryption on certain payload elements kicks in automatically. Now, as I said, this is a really simple language, right? So noise tries to be secure by default. It tries to be mistake-proof. And so a lot of the operations within noise, the cryptographic operations like encrypt and hash or HKDF, the state objects like cipher state, symmetric state, handshake state, and by the way, each of these is contained within the one coming after it, or the actual state transformations are all defined in the spec, and there's a bunch of rules that says, well, oh, if an E token comes after a whatever token in that position, well, then you need to do a mix hash. And so if you actually implement things according to those rules, you are supposed to end up with a secure channel protocol that does the best it can with the amount of keys available to it according to what you yourself wrote here, right? And so that is the goal of noise. Now, noise is used in many cool applications, such as WhatsApp. Have you heard of it? People use it. And so it uses noise. And also WireGuard, which is a cool new open source project by Jason Donenfeld. You should check it out. It's an open source project. It's a VPN. It also uses noise. And so now, noise, as I said earlier in my talk, is a protocol framework. There's not, like in TLS, you have a single protocol. It's called TLS. In Signal protocol, you have a single protocol. It's called the Signal protocol. In noise, there is no such thing. There's a million protocols. There's an unbounded number of noise protocols. And so the noise authors knew this, of course, and they developed a grade-based system for trying to understand the security goals and what exactly each noise handshake pattern achieves at which potential message in terms of authentication and also in terms of confidentiality. So there's 3 authentication grades. We expand these to 5 in our analysis, but that's not important. And there's 6 confidentiality grades. There's also something called identity hiding, because noise actually will also encrypt your long-term identity key or static key opportunistically. And so identity hiding is whether it will reveal to an observer your identity key or not. We don't analyze that, but it's important because the noise spec certainly talks about it. So in terms of authentication grades, you can start with level 0, which is just no authentication. This payload may have been sent by any party, including an active attacker. And so here, this message has a 0 authentication grade. And you can go all the way up to 2, which is that assuming the corresponding private keys are secure, this authentication cannot be forged. With confidentiality, you can start with 0, which means that this payload is sent in clear text. And you can go all the way up to 5, which means strong forward secrecy, assuming the ephemeral private keys are secure, and that, of course, the recipient is not being actively impersonated in the middle of the session. Then this payload just simply cannot be encrypted. And you have a lot of weak forward secrecy stuff in between. So for example, this last message, which by the way has no tokens, which means it's just a payload message. There's no fancy Diffie-Hellman stuff. I just spotted Mr. Whitfield Diffie while saying that. What a coincidence. Sorry. I am very nervous at the moment and therefore saying things that I shouldn't be saying. I don't know whether you've noticed that physiological effect that I'm exhibiting at the, all right. So there are so many security goals, 50 plus handshake patterns in the spec alone. So how do we verify all of these protocols against these security goals? I mean, if you just look at the noise spec alone, you'll see that there's about 60 or 55 noise handshake patterns defined in the spec. So if we have a security query, like trying to verify something based on every one of these, then that's like 500 security queries that we're going to have to manually prove, right? Because we're cryptographers, want to be rigorous, want to prove everything. And so that's a lot of them. You're going to spend a lot of time. You're not going to see the world. You're not going to visit Japan. It's going to be a problem. And so noise also, let's not forget one of the more important parts of noise, which is that it allows for use case specific protocols. So maybe TLS shouldn't be the answer to everything. Maybe you have a use case where you can't really obtain the keys at the right time. You can't obtain a certificate at all. You can't do some of the stuff that TLS requires, or you just want something more streamlined. And noise really allows you to do this because it allows you to design your own protocol that can really fit your use case. So how can we ascertain in this even more interesting context which security promise any noise handshake pattern can give, right? Especially if you want people to design their own. What an interesting problem. Well, introducing for the first time in the United States, Noise Explorer. Wow, it's amazing. It allows you to verify any noise handshake pattern. How does it do that? There's an unbounded number of them. Well, you can design noise protocols and immediately obtain 2-spec validity checks and helpful visualizations. Pictures, everyone likes that. You can generate models for formal verification. Now, this is the more interesting part. So you can enter any description for any noise protocol pattern, noise handshake pattern, and you can immediately from there obtain a formal verification model, and you can just get the answer to the security queries. Does this achieve authentication security grade 1, 2, 3, 4? Does this achieve confidentiality grade 1, 2, 3, 4, 5? Immediately. Well, after running the formal verification model, which in many cases is not very immediate, but you get the point. And these are run with top-level processes with the security goals already generated, and also in a very ambitious model that includes a compromise principle, right? I'll get to what that means in a bit. And you also have, because some of these models take a very long time, you have a Noise Explorer compendium. So I've already run a lot of these models, and there's a compendium that shows you the results for the models that were run. And this is very new, announcing today for the first time. Very soon you'll be able to generate implementations. So Noise Explorer will also, you just enter the noise protocol handshake description, which is just the little things I put on the right earlier. And from there, you will immediately obtain a full implementation. I'm almost done. I'm just doing interop testing on the JavaScript part now, but I'm also going to do Go. And other languages could be there. I didn't pick these 2 languages I just know them well and use them a lot. But it could do C++, Swift, Java. It's fine. Any language, really, in the future. This is all open source software. You can all contribute to it. You're most welcome. But what is formal verification with ProVerif? So I studied in Europe. In North America, formal verification is, maybe I'm wrong, but it's not as well known in my experience. And so Automated formal verification essentially is an approach to beat this thing that's happening a lot in applied crypto, which is to code first and specify later, if ever, right? A lot of crypto systems, if you look at the history and evolution of TLS, so TLS 1.0, 1.2, 1.1, people really were being very pragmatic about it. And then there were a lot of attacks, drown, smack, freak, whatever, and poodle, and all of those attacks. And so in TLS 1.3, the formal verification and there was a lot more academic involvement. And so people are moving towards a specify first and code after methodology, which maybe is more fruitful. Now, there are two main models for formal verification. You got the symbolic model and computational model. I'm not going to get into those a lot, other than to say that we're using the symbolic model, where essentially it's fully automated. The computational model acts as a proof assistant a lot of the time. And we can model protocol flows and try to find contradictions to security queries. So we model the flow of the protocol. We say, all right, well, the IK noise pattern is going to be executed between Alice, who's talking to Bob and Charlie, Bob, who's responding to Alice and Charlie, and by the way, Charlie's fully compromised and controlled by the attacker. And there's an unbounded number of messages and an unbounded number of sessions. So what are the security goals that are accomplished in that setting? And then we ask, well, we formalize what authentication 1 means and what authentication 4 means and so on. And we say, well, which one of these are going to be met? So that's what we're trying to do. And we're trying to do that with ProVerif, which is the tool for symbolic automated formal verification developed at INRIA in Paris, where I did my PhD with, it's developed by Bruno Blanchet and his team. You can check it out. It's open source software at this URL. There's a very comprehensive manual also if you're interested in getting into it. And I strongly recommend you do. It's really cool stuff. So if you're looking for examples on how to use ProVerif, you can just generate a model using Noise Explorer, actually. But also, for other use cases, I recently defended my PhD, and there's many, many, many use cases on ProVerif. I did a lot of stuff with ProVerif. You can download that and check it out. So in ProVerif, actually, what's interesting in the symbolic model is that many notions of having information inside cryptographic instructions are reduced to basically symbolic elements. So essentially, all cryptographic primitives are perfect primitives. A hash function, as a matter of fact, is a perfect one-way function every time. There's no such thing as a hash function that's vulnerable to a length extension attack. At the same time, so if you look at the right here, you'll see that Diffie-Hellman expanded initiation takes 2 keys and gives you a key. And actually, if you have G to the A to the B, it is equal to G to the B to the A, right? And so this is a very naive encapsulation of Diffie-Hellman, but you can kind of see how this is represented using the symbolic model, and I hope this is useful. So this is how we represent encryption. So you get a key, a nonce, a bit string, and a bit string, and you get a bit string, right? And so this is, for example, the key, the nonce, the authenticated additional associated data, and then this is the plain text, and you get for text, right? And decryption is actually a reduction of that to deconstruct it back to the plain text if the key and the nonce and the associated data all match, and then you get a Boolean that says whether the decryption was valid or not. And so, for example, this is a naive way to capture ASGCM or XChaCha Poly 1305 or any similar primitive, right? And then we essentially have a common state management library, which is written by hand and not generated using Noise Explorer, but that's it. And the rest is fully generated using Noise Explorer. And so our findings where we analyzed more than 50 noise handshake patterns taken from the noise specification itself. And we confirmed that so Trevor and his team already had numbers for many of these patterns, not all of them, but many of them. And we confirmed that these numbers were correct. So great, we were able to say formally that these predictions were correct. And we were able to offer a new verification for new patterns that are always increasing. And we essentially also showed so noise has very intricate validity rules that can sometimes, you can sometimes make subtle mistakes, and this is being worked on. But we showed that if you do make a mistake in the validity rules that are in the noise specification, then some very subtle attacks can be found. So you better have a way to follow those design rules so you don't come up with some broken or less secure noise handshake patterns, secure channels. So we also contributed some improvements to revision 34, which is currently the latest revision of the noise protocol framework. And we defined now we have more well-defined pattern validity rules to help avoid misunderstandings. And we also, of course, have higher assurance for fundamental pattern security grades based on the fact that we have all of these numbers, all of these grades being assigned, and that now, unlike before, they are related to actual formal verification, not just Trevor and his team manually for every one of them determining what is the correct grade. And we added, well, I had forgotten that number, but we added 23 deferred patterns, security grades for 23 deferred patterns. But I want to talk about something else that's very interesting. So I said that there's a new feature, which is currently in beta, which is giving these JavaScript-generated noise patterns. So let's look at the advantages of that when comparing it to TLS. So boring SSL is the TLS library that's used by Google. And and I hope this is a correct assessment, please correct me if I'm wrong. I think that if you look at the lines of code and consider only the protocol parts and the crypto parts, it comes to around this. So close to 250,000 lines of code. So maybe, boring SSL is not optimized maybe for ultra confined small code stuff. So let's look at bare SSL, which is supposed to be optimized, right? So bare SSL is around 50, less than, I think 40, 30 to, I can't read the numbers here. But yeah, it's much smaller. It's less than 50,000 lines of code for the crypto and the protocol parts. However, if you look at IK, which is actually one of the more elaborate noise handshake patterns in the spec, there was supposed to be an explosion sound, but yeah, hold on. It's supposed to be like, but it doesn't do that. All right, so yeah, as you can see, and this is, by the way, a conservative estimate. I think it's going to be smaller than that, but this is about 4,000 lines of code if you include all the protocol stuff and all the crypto primitive stuff. But I'm actually, I'm giving myself a fair bit of buffer in case it turns out to be more than it actually is right now, which is smaller than this number. And so you end up with less lines of code to audit, less states that an attacker can jump to in case they find a state machine attack or a buffer overflow or similar. And that is great because it means that we can build a system that takes less trust from us in order for us to trust it. So that's good. All right, so let's do a demo. So I said a lot about Noise Explorer being a framework, so that means that I can demo it. So let's do that. All right, this is Noise Explorer. You can open it right now on your laptops if you go to noiseexplorer.com. So please do that if you like. And you can fully use it. So Noise Explorer is essentially, this is the title page that you'll come to. The pattern here that's already contained, and you can just type your own pattern. You can type your own, potato pattern, and you can just say, sends a static key, and then in return there's a static key, and then you're doing a static Diffie-Hellman. Aha, it says that one of the validity rules was not matched. So the validity error that it found, after an SS token, the initiator must not send a handshake payload or transport payload unless there has also been an ES token. This is one of the rules that was added to the noise specification to ensure that some properties are met. And so we can say that, all right, well, each of these is also sending an E, and then we're going to do ES. Noise handshake patterns should not contain key shares that are not subsequently used. Which ones am I? Oh, yeah, of course. There we go. And so there you get a nice illustration. You're sure that this is valid to spec. And all right, I just designed my amazing protocol. I can just click this button, and it'll download a full formal verification model that I can then run using Proverif, and it'll give me a result. I'm not going to do that right now. What I'm going to show you is the results in the compendium. So if you open the noise pattern analysis results, you can just type the name of a pattern if you've already seen it in the spec. I want to see, for example, the results for XK. All right, so I just click here. Great. These are, you can re-download the model here and rerun it if you like, but these are the results that were generated before. And so, for example, I'm interested, and you'll see that, by the way, you'll see that these results are explained using an accessible, literal style, which I really worked hard to ensure, because I think that's important. You can read it. It's English. The responder is initialized. This is all generated. I didn't write this. The responder is initialized with a pre-shared long-term static key, which is assumed to be pre-authenticated. Message A, sent by the initiator, does not benefit from sender. And so you can actually read it in a literal style. It flows well. You're not reading math formulas the whole time. But if you want to read math formulas, then be my guest, because you can just click this button for message C. You get the message over here in large numbers, large letters, and you see like, okay, well, message C. And again, this is all generated. Noise Explorer, the tool, will generate these reports for you straight out of the ProVerif models once you analyze them. So none of this is written by hand. And this is useful, I think, for you to allow you to reason about this protocol that you're designing. And so message C is the third message in XK1. It is sent from the initiator. And so here you can see the actual syntax in the applied PyCalculus for the message as it's being sent, as it's represented in the ProVerif model. You can see exactly how each token in the message is processed by the initiator. So you can see that, all right, well, he's calling, or she is calling, encrypt and hash. There's, if any prior Diffie-Hellman shared secret was established between the sender and the recipient, this allows the initiator to communicate their long-term identity with some degree of confidentiality. I'm referring to identity hiding here indirectly. And so you got SE, you got mixed key, you got all of these things that are being called here. And then for receiving message C, there's the same thing, the same treatment. And so you can also see exactly which authentication grades are being passed, right? So authentication grade 1, which here you're like, okay, well, in the event that Bob received a message from Alice in this part of the session, and that was the message, then it must be true that Alice must have sent a message to at least someone, which could be Bob, could be Charlie, and then that someone is upgraded to, in other stages of authentication, to necessarily be Bob, right? And so that makes it achieve a higher grade of authentication. And you can see exactly what each query means, how it is written in the formal verification model, and whether it was passed or failed. And for confidentiality, you will also be able to see that well. For demonstration purposes, I wanted to be optimistic and pick something that passed everything, but you can just open any other message that is less great, like this one, which is horrible, because all we're doing was just sending an ephemeral key like that. Obviously, there's no authentication. So fail, fail, fail. You'll see also that there's no stuff, no good stuff here. All right. And that's it. That's really Noise Explorer. I'm a bit over my time. All right. So great. The future of noise, very quickly. So small use case specific protocols. The entire standard library of noise is around 1,000 lines of code. And specific handshake patterns can be smaller. As I said before, I'm really giving myself a lot of leeway and also including some crypto primitive stuff. There's a great post by David Wong that compares noise to existing work. And it's really cool because it gives you an intuition of how this stuff can be used in the wild. Even here at Real World Crypto, I've already met people who are using noise for stuff that I didn't know about. Which is great. And it has the potential to be much smaller and more use case specific, have a more use case specific state machine than TLS or similar. There's upcoming work in noise. There's signatures being added that currently doesn't support signatures. There's stateful hashing and symmetric crypto, which is having an overhaul to include stateful hashing. There's something called noise socket and NLS, which is being worked on. And to be honest, I'm not particularly familiar with what that does, but you can check it out. It's related to noise. And well, that part is what is coming soon, part of Noise Explorer. It's essentially an implementation of noise that generates implementations in JavaScript and Go. So I think that the real potential of Noise Explorer is to be the ultimate online compendium for reasoning about, designing, studying, implementing, and verifying noise handshake patterns. I want to present my special thanks to Bruno Blanchet, the creator of ProVerif, and Trevor Perrin, the creator of Noise, for their assistance with this work. There's also related work. Benjamin Lip, also studying at the same lab I studied at, Prosecco in France, is working on a WireGuard automatic verification using CryptoVerif, which uses the computational model. And I also want to thank my co-author, Kartik Bhargavan, who's here in the audience and was indispensable in the creation of this work and my general higher level education in general. So please check out Noise Explorer at this URL. And this paper, and don't forget to hit subscribe and click that like button for more videos, and check, and make sure to click the bell icon for, all right. Thank you.
Yeah. Okay, I think we have time for just one question. So we're going a little bit over. One question, anybody? Okay, well, all right, Nadim, thank you very much. All right, the next presentation is going to be by Cesar Gali from Google, who's going to talk about application layer transport security, which you may have heard of from previous talks by Google, but this is going to be a deep dive. So, thank you very much. Oh. Okay, let me know if you need this one.
Thank you. Hello, everyone. I'm very pleased to be here and present application layer transport security. It's a system that was developed and is used at Google. So to start with, a lot of distributed systems in the current internet use secure communication protocols to basically protect the data that is in transit between all entities of the system. At Google, we use something called Application Layer Transport Security, or ALTS, mainly to secure remote procedure calls, RPCs. Why did we make this binding between ALTS and RPCs? The reason is because RPCs are widely used at Google. There's roughly 10 billion RPCs every second in the production network. So you can basically see the scale and why the reason for developing something that adopted the scale, basically. ALTS provides transport security with zero configuration. Basically, nothing is needed from the application developer or the user to use ALTS. It's enabled by default for all RPCs. It's also friendly to service replications, load balancing, and rescheduling across production machines. So why did we come up with ALTS and not use TLS, for example, which is very widely used everywhere else? So to answer this question, this goes back to 2007, where ALTS was first, where the development and design of ALTS began. Basically, TLS back then did not fit the security model of Google, nor the scale requirements. And it was decided that using TLS, it was decided that TLS implementation is complicated for Google use, especially because it supports a lot of legacy flows and protocols. But theoretically, if you think about it, or as they thought about it back in 2007, TLS could actually have been modified and used instead of developing a new protocol, but they realized this for the sake of simplicity and long-term support. Creating something from scratch had a lot of advantages. Some key differences between ALTS and TLS are, and the list is not, there are more things than what's on the list, but basically the trust model is different, and I'm going to be talking about this trust model in a few slides. ALTS is simpler in design and implementation, which allowed for easier analysis of bugs and security vulnerabilities. And last but not least, ALTS uses protocol buffers heavily, which is widely used in Google. It's more suitable for Google production network. ALTS design basically is built around this vision. It was designed to be a highly reliable, trusted system that allows for service-to-service authentication and security with minimal user involvement. So we materialized this vision in the following guideline principles. First, ALTS is transparent. It's enabled by default for all RPCs that are issued in Google production network. No need to worry about any key management, rotations, issuance of certificates, all these kind of stuff. And the authenticated peer information is propagated to the application at the end of any handshake in case applications want to use, for example, finer grade authorization. ALTS uses state-of-the-art cryptography, and we try to keep it up to date. For example, AES GCM with auto-rekeying. And since Google controls ALTS and controls all entities that are running ALTS, it's easier to basically roll out new crypto primitives, new crypto protocols, and basically stop supporting old ones. The ALTS also authenticates identities and not hosts, and One important thing is that mutual authentication is enabled by default. It's not optional. All identities in ALTS they have corresponding managed certificates that are deployed periodically to workload without the application. They're deployed to workload by the workload scheduler, and that doesn't involve the application or the developer of the application. ALTS supports efficient session resumption for better scalability, and the connections in ALTS are long-lived also to support the huge scale of Google. Last but not least, ALTS is simple in design. It's specifically tailored for service-to-service communication patterns and does not support legacy protocols. So how does the trust model of ALTS look like? As I said earlier, ALTS authenticates identities and not hosts. Everything is around identities. Every network entity, a machine, or a workload has an identity with a corresponding certificate. This identity, along with the certificate, is used in the peer authentication. The model pursued here follows this simple example. Major production services should be run as SREs, should be run as identities managed by the SREs, while the development versions of these services should run as test identities managed by the SREs and the developers. Similar to authentication, authorization policies are also written around identities. An example of an authentication policy could be production services do not trust the development version of the same services, which kind of makes sense. There are 3 types of credentials in ALTS. They're all expressed in protocol buffers specifically, and these are master certificates, handshaker certificates, and resumption keys. Master certificates are signed by a remote signing services, which is the root key with the root of trust. They contain RSA keys, and the associated private key of these master certificates is used to sign handshaker certificates, which are the second type of certificates. Master certificates are usually issued to production machines and schedulers of containerized workloads. Second type is handshaker certificates. These are signed by the master private key. They can be created locally for system services, or they can be and provisioned by the scheduler of containerized workloads. They contain parameters used in the ALTS handshake, and they contain the master certificate that is used to verify them to simplify the verification process and make it more local. So given these 2 certificates, we can envision the certificate chain of ALTS. The root of trust on the left is the signing service verification key, which is used to verify the master certificate, which is used to verify the handshaker certificate that are eventually used in handshakes. The last type of credentials are resumption keys. These are secrets used to encrypt resumption tickets. They're identified by resumption ID that is unique for all workloads running in the same data center as the same identity. So basically, if there are multiple servers that share the same identity and they run in the same cell of data center, they all have access to the same tickets, resumption tickets. Certificate issuance. Any entity that needs to use ALTS or perform an ALTS handshake, it needs to have a handshake certificate, basically. And the first step is for the issuer of the certificate to have a master certificate, because we need the private key of that master certificate to sign the handshaker certificate. This is a simple process that involves the certificate issuer talking to the signing service. It sends basically a CSR with its identity. The signing service would create the certificate, sign it, and send it back to the issuer. And now the issuer can start creating handshaker certificates. Before I continue with how certificates are created, let's look at the 3 different categories of certificates in ALTS. So I said that we have something called master certificates that are used to sign or verify handshaker certificates. These are types of certificates. But now, who are the certificates issued for? They can be issued to humans. So these are called human certificates, and basically they're issued to developers, and and they're used to basically ALTS secure all RPCs that developers send to the production network. These certificates are usually short-lived. They last for less than a day. The second category are machine certificates. From the name, they're issued to all machines, all production machines. These are master certificates, so basically their corresponding private key can be used to sign handshaker certificate. The machine master certificate are rotated every few months, while the machine handshaker certificate are rotated every few hours. So relatively, they're both relatively short-lived as well. The last category is the workload certificates. These are basically handshake certificates. They can be used to perform ALTS handshakes. They are issued to workloads in the production network, and they're issued by Borg. Borg is they're basically issued by Borg Master, but Borg is the cluster management system that is used at Google. And these certificates are rotated every 2 days on average. So going back to how certificates are generated, I hope the font is not too small for the people in the back. So the first step, as I said, we need a master certificate, and this is here. The left machine is the Borg master machine, and this is the flow of how a handshaker certificate ends up on a workload. So the first step, the Borg master would get a master certificate machine, a master machine certificate that is used to create a Borg master handshake certificate, which the Borg master can use to talk to other services like the signing service. And then the Borg master would create a Borg workload master certificate. This is step number 3, gets it signed by the signing service. And now this is the master certificate that is used to create all handshake certificates for the workloads that are created by this Borg master. Borg master is basically the centralized entity that creates all workloads in a specific cluster. Whenever a new workload needs to be scheduled, the Borg master would create a new handshaker certificate, signs it using the Borg workload master certificate private key, master private key, and push that down to the Borg workload, and that handshake certificate can be used by the application of that workload to do ALTS handshake. The protocols that are used in LTS, basically there are 2 main protocols. The first one, as you can tell so far, is the handshake protocol, which is basically a session key exchange protocol. And the second one is the record protocol, which comes after the handshake. And basically it's used to provide confidentiality and integrity for all data transmitted, and it supports auto-rekeying. The handshake protocol is a simple Diffie-Hellman-based protocol. As I mentioned before, all entities in Google Production Network that needs to use ALTS, virtually all entities because they all issue RPCs, they have credentials. They have credentials that have identities, ALTS identities with some other parameters like ECDH keys that are rotated frequently. These are the parameters that are used in the handshake. The handshake protocol also supports perfect forward secrecy with some additional ephemeral keys and session resumptions. And at the end of the handshake, the client and the server would have negotiated a session key and decided on what next protocol to use from now on. This is done using using 4 messages: client init, server finished, and client finished. So the first step is for the client to send a client init message that contains its certificate, its handshake certificate, which contains the identity of the client, a list of record protocols that the client supports, and optional resumption ID and resumption tickets. Once the server receives that, it verifies the client certificate, checks the identity, and choose one record protocol that is from the list of protocols provided by the client that is supported by the server. Then it computes a Diffie-Hellman exchange result and derives the following session keys, or the following secrets. The first one is the session key M that will be used by the record protocol. The second one is a resumption secret that will be used to encrypt, that will be put in the resumption ticket. And we'll talk about resumption in a few minutes. And the last one is an authenticator secret, which will be used in the next message. After that, the server would send its server init message now, which contains the server identity, the server certificate, which contains its identity, the chosen record protocol, and optional resumption tickets. Also, the server, since it's finished its part, it will send a server finished message containing HMAC over a predefined bit string, and this HMAC is computed using the third secret that is derived, which is secret A. Once the client received this, they received the first message, the first of these two messages, the server init message. It can verify the certificate. It derives the same MR and A, and then when it receives the server finish message, it uses the derived A to basically verify the authenticator on that message. And at this point, the client has all the information to start using the record protocol. Basically, it can send encrypted data using the secret M. And the last message is sent by the client, which is the client finished message, which terminates basically it indicates the end of the handshake protocol. It also contains an authenticator that is computed with the same secret. Once the server and additional resumption tickets. Once the server receives this, it verifies the authenticator, and now the server can send or receive data encrypted using M, the secret M. The next protocol is the record protocol. It's basically the one that kicks in after the handshake finishes, and it protects the confidentiality and integrity of all traffic after the handshake. It's basically a collection of encryption schemes. There's no one scheme that we support or that ALTS support. It provides support for multiple schemes and with different key sizes and features. The client sends its preferences in order, and the server would choose the first one that matches its local preference or local configuration. The reason for this exchange between the client and server and have a list on the client and the server is to allow both of them to have different preferences, and it makes it easy for us to roll out and roll out new crypto schemes and deprecate old ones. Session resumptions, I mentioned this several times. It's used to resume connections without expensive asymmetric cryptography. ALTS handshake, as we saw in the 4 messages during the handshake. During the handshake, clients and servers can exchange resumption tickets that are stored either on the client side or on the server side. And these tickets are identified by resumption ID, which, as I mentioned earlier, it's unique to all workloads in the same data center, running as the same ID. Tickets are encrypted with a symmetric key, so they can only be decrypted by the entity that generated the tickets. These symmetric keys are associated also with the same resumption ID, and they're also distributed to workloads based on that ID along with all handshake certificates during workload setup. There are 2 types of session resumptions. The first one is where the tickets are stored on the client side, and the other one is where the tickets are stored on the server side. I'm not going to go into details for lack of time, but I'll be happy to talk about that offline afterwards. And last but not least, everything comes with trade-offs, and of course, ALTS is one of these things. So there are multiple trade-offs that were made during the design of ALTS. First one is KCI, key compromise impersonation. ALTS is susceptible to KCI attacks. So basically, a compromised workload private key or resumption key would allow adversary to impersonate any other workload to this workload. But this is not considered an attack per se on ALTS because it's part of the resumption threat model. In fact, there's a variant of ALTS that protects against KCI attacks, but it can only be used in an environment where resumption is not supported. ALTS is not designed to hide the identities of the peers. Therefore, none of the handshake messages are encrypted. And that's by design. What did we learn from ALTS during the years? First one is changing authentication system in production is very hard without breaking the production system. What's even harder is changing the trust model of a production system while keep it running. Another lesson learned was diverging from a standard is very challenging, and it's a very delicate balance. The questions are, do we do hacks to stay in standards, or do we diverge completely from the standard, or we do something in between where we do our own things and we keep we stay compliant with the standard and basically compliant with the standard. And the last one is key exchange and the record protocol are the small part of the entire system. The challenging part is identifying the security boundaries and adversary models. And also another challenge is key management, rotations, and revocation of certificates in a way that does not involve users of the application or the application developers. Thank you. And if you are interested in more information, you can check out the white paper that was published on Google Cloud Security website. Thank you.
Any questions?
After you've negotiated the session key, I'll call it the session key, you said specifically in your slide that from then on all the messages are encrypted.
Yes.
Do you mean authenticated and encrypted, or just encrypted? And if so, why not authenticated?
Yeah, so they're authenticated and their integrity is protected as well.
Okay, that to me is more important in some sense.
Yeah, it's encryption and integrity.
Had two quick questions. One is the authenticated string that's added at the end of the server init and the authenticated string added at the end of the client init. All right, is that right? Or
yes.
There's an authenticator. Is that used similar to what we are doing in TLS 1.2, wherein to add context to the handshake part of the protocol so that it doesn't get replayed later?
So the part that is protect against replay attacks is the computation of the Diffie-Hellman exchange because it involves a transcript from the session. And the resulting A secret is used to compute the HMAC. So basically, indirectly, that HMAC contains information from that session specifically.
Right. Okay, and are the session tickets encrypted at the end? You showed the session ticket, yeah.
Sorry, where?
Session tickets. Are those encrypted?
The resumption tickets,
yes.
They're encrypted with a different key that is only available to the party that can access these tickets.
Okay, thank you.
No problem. Thank you.
Thanks. Thanks for the very nice talk. Did you do any formal security analysis?
Yes, that was done a few years ago. I don't have access to it at the moment, but yes.
But it's secure.
Yes. Hopefully.
Okay, let's thank Cesar again.
Thank you.
And right now there's going to be a short break, so come on back at 2:50 for the next session.
Hello, hello. So despite the advertisement to the contrary, there is no break. I'm so sorry. And you can be mad at Nick for getting your hopes up. So we're powering right through to the next set of talks. We're going to be talking about passwords, and here we'll hear about Opaque, a new client-server password authentication standard from Ugo. Please take it away.
Thank you. Yeah, so this talk is complicated technology. Can you hear me? Okay, so this talk is about a password authenticated key exchange protocol called Opaque. It's something I want to present because I think it's a good idea to standardize on a strong protocol, and this one has some interesting properties and represent a good candidate for standardization. This work joined with Stash Yaretsky and Xiao Xu. We presented it at last Eurocrypt, and I also have an internet draft on describing the protocol. First, I want to introduce you to Xiao Xu, one of the co-authors. Xiao is finishing his PhD this year and will be interested to hear about the job opportunities. Huh? You ruined my joke. Now, so this is Xiao, and the joke was, if you don't see him, well, you will have to decide which one in the picture is Xiao. Passwords. Passwords have become a crucial part of our information security, and love them or hate them, you cannot ignore them. If you think that passwords are about to disappear from the world, then this talk is not for you. I was in that camp 25 years ago, and I was more than 25 years old. And life and my white hair have taught me that, no, they are not disappearing. So let me discuss some of the attacks against passwords. Some are unavoidable, some are avoidable. The two main unavoidable attacks due to the low entropy of passwords are online guessing. You know, if I can guess a password, then I can impersonate a user. The mitigation for that is throttling, limiting the number of failed attempts in password authentication, and of course using also second factors. The other very, very relevant and effective attacks on passwords is offline dictionary attacks that happen when an attacker breaks into a server, finds the password file, and now it sees a set of hashed passwords, and now it can run a offline dictionary attack on that list. That's unavoidable. What will be important is that this unavoidable attack will start only at the time in which, after the attacker breaks into the server, and not before that, like by building pre-computed dictionaries. So the mitigation here is salting. There are a bunch of avoidable attacks. So one of them, which we owe to the password over TLS, which is what the majority of us do for password, encrypting password and sending them over TLS, is what they call plain text password visibility. The server, when it gets the encrypted password, decrypts the TLS and can see the password in the clear. Of course, anyone on the way that can somehow either break TLS or just have a legal opening to see what's in the plain text, such as termination points, CDNs, middle boxes, all of these, the password will be visible to them. In particular, phishing is a result of this password visibility. The other thing that some implementations don't avoid but are avoidable is this pre-computation dictionaries that I was mentioning before. Again, if you don't solve the passwords, that's something that is a weakness that definitely is avoidable. This brings us to the notion of asymmetric PAKEs, or APAKE. An asymmetric PAKE is a password authenticated key exchange in the client-server setting. This is in contrast to symmetric PAKEs, which is between two peers where both of them remember or store the same password. In the client-server, the user will have a password and the server will store some one-way image of the password. Now, to be an APAKE, we want some security assurances. So first one is no pre-computation attacks. It will be open to offline dictionary attacks upon server compromise, but nothing that can help that attack before breaking into the server. We will want the plaintext password to never be visible to anyone outside the client domain, in particular not to the server. And we also ask it to be PKI free, not depends on PKI. We want that the only thing that the user has to take with him and trust is the password and nothing else. So these are the properties that we want for an APAKE. Opaque is a protocol that I'll discuss here and achieve these properties. Actually, quite surprisingly, it is the first protocol to achieve all these properties. We have seen over the years many asymmetric PAKEs being presented both in theory and in practice, but none of these protocols is actually secure against pre-computed dictionaries. And the reason is that these protocols either don't use salt at all, so they are trivially open, or if they use salt, they transmit the salt in the clear between the server and the client. Therefore, the attacker can learn the salt and build a targeted dictionary. And again, this is even true for some protocols that were proven secure, but they were proven secure in a weak model that allows for these attacks. And it is also the case for many of these more practical protocols that have been suggested as possible standards. And it's a PKI-free protocol. The only place where you need to assume PKI or secure channels is for the password registration stage, in which the user needs to be able to identify the server it is storing the password-related information. And the password will never be in the clear outside the client domain, not even during password registration. And in particular, this foils phishing. So these are nice properties. They are also proven. I will talk about that. And there are some other interesting properties of the protocol. But first, let me give you an idea of how this works. So for that, I need to first introduce this notion of oblivious PRF that some of you may be familiar with. Anyway, the PRF, or pseudo-random function, is a keyed function that is indistinguishable from a random function for anyone that doesn't have the key. An oblivious PRF is a PRF that, in addition, has a protocol that a user can run with the server, where the user has an input, the server has a key. At the end of the protocol, the user learns the output of the function on its input without the server learning anything, meaning nothing about the input of the function or nothing about the output of the function. Okay? So with this beautiful crypto primitive, we can build now opaque. And I'll show you the basic idea. The basic idea is not new. Actually, this originates with the beautiful and seminal work of Ford and Kaliski. And the first implementation of this idea into opaque is due to Boyen. There is some other related work. None of these works actually have the generality of opaque that I will show, and none of those have any proofs of security or even a formal model of opaque security. So, okay, so now we had the OPRF. So the idea is really, really simple. Once you have the OPRF, what we are going to do is the user and the server will run an OPRF. The input of the user will be the password. The output will be an output of the PRF, which is a strong cryptographic key because it's a pseudo-random value. So the user basically exchanged its password for a strong cryptographic key, while in the process, no one, including the server, learns anything about the password or anything about the key that the user retrieved. So now that the user has a strong cryptographic key, it can use it as a private key in a key exchange with the server. Okay? So that's everything. It's a key retrieval stage, and then using that key to bootstrap a key exchange session. In the case of Opaque, we will build Opaque on the basis of any OPRF and any key exchange protocol. We'll be looking at public key exchange protocols where the user will have a public and private pair. The server will have a public and private pair. Now, instead of using the retrieved key as a private key, what we do is during password registration, the user will encrypt its own private key and store it at the server. Also, we'll authenticate the public key of the server in the same envelope. And during login, it will get back the envelope. We'll run the OPRF to get back the key that encrypted that envelope, decrypt the envelope. Now it has its own private key. It has the public key of the server, and both can run a key exchange. That's basically all that is in the protocol. Now it's about details, and the devil is in the details, and definitely there are details here that can change this from secure to insecure. But this is the idea. So basically, you can see, think of Opaque as a compiler, basically from any oblivious PRF and the key exchange to an APEC. So when I say any key exchange, actually it is key exchange with the KCI property that was mentioned in previous talks. I don't want to get into the details, but essentially what it means is, I mean, it's the property that ensures that if you break into the server, you will be able to impersonate the server to the client, to the user, but not vice versa. Okay, so how do we actually build Opaque? We start with the Diffie-Hellman OPRF, which is the most efficient implementation we have of OPRFs. This is nothing other than blind Diffie-Hellman. So the PRF will consist of the user will take its input and will compute on it a hash function h prime, which maps that input, which in our case will be a password, into a random group element. And that value will be raised to the power of k, where k is the PRF key that in our case will be held by the server. Now, to compute the function, the user will take this h prime x, the mapping of the password to the group, will multiply it by a random group element g to the r, will send this to the server, which will raise the received value a to the power of k. This will go back to with the client, which by the magic of Diffie-Hellman and algebra and all this stuff, will be able to actually deep-blind the value and get h prime x as required. Doesn't matter if you follow this or no. The important point here is to see that all the server sees in this interaction is this value a, which is something times a random group element. Okay, so A is a random group element, and the server has learned nothing in the information theoretic sense of nothing. And so X and the output of the function on X is perfectly hidden from the server and therefore from anyone else. Okay, one thing I want to say is about the complexity, the performance of the thing. Then the communication is just a single round. The computation is one exponentiation for the server, two for the client, where one of them is with a fixed generator, and one hashing into the curve. So now we can build Opaque. Opaque consists of running the OPRF between the user and the server, as I mentioned before, in this case the Diffie-Hellman OPRF. In parallel, the server will be sending this envelope where the user has these encrypted values. And also in parallel, they will run an ephemeral Diffie-Hellman. Okay? at the end of the thing, the user has learned the output of the OPRF on the password. It can use to decrypt the envelope, and now it have its own private key, the server public key, and with it, it can compute a session key depending on the specifics of the key exchange protocol. And same thing for the server. If, for example, we implement this with the key exchange being HMQV, then you get this full protocol in a single round with forward secrecy and the other properties of HMQV. And the computational cost is about 2.5 variable-based exponentiations for both client and server, plus a hashing to the curve for the client. So this is one instantiation. We have more instantiations. By the way, if you use HMQV and you want to get explicit user or client authentication, you need to add one more flow, a message with a MAC from the client. But, and there are other implicit authenticated protocols that you use, usually with a little bit more of exponentiations. Another instantiation is with signature-based protocols. In particular, if you do it with Sigma, then you will have the private key of this client and the server will be signing keys, and you will need 3 messages to exchange these signatures, but the OPRF itself doesn't add any more messages that Sigma had in the first place. Now, very importantly is that opaque can work well with TLS. It relatively blinds smoothly with the 3-flight exchange of TLS 1.3. Actually, what you're going to do is you need to take TLS 1.3 as is, plus some extensions to accommodate the Diffie-Hellman OPRF values. And the signatures that you will have a signature from the server and a signature from the client will, instead of being certificate-based signatures as in the regular TLS, these will use the keys that are being stored by opaque itself. But other than that, it's the same exact logic of the protocol. Now, in this case, I'm sending the account information, user ID, in the first message, unprotected. If we want to protect that, then you either need some keying material to run a 0 RTT or a resumption key. If you have that, then this protocol is perfect. If you don't have that and you want to protect account information, then you will need to add a 1 RTT round trip to the protocol, where you first do a regular TLS authentication of the server to exchange a key with which you protect the user account information. Here, you will be using a server certificate, but you will only be using it for the privacy of account information, not for security of the key exchange protocol itself. Now, if you do that you put both opaque and 1 round of authentication, of certificate-based authentication of the server, what you actually get is this edging property of TLS, which now your protocol will be secure as long as either the PKI and TLS are functioning correctly, and or the password is secure. So even the password is secure and PKI is not, you're still getting security. This is what I call going from TLS protected passwords, which is what we use today, to password protected TLS. This is okay. About opaque security, well, we proved security in a strong opaque model that ensures all the properties that I discussed before. By the way, I was saying that salting is necessary for the things. There is no salting in the traditional sense, but the OPRF key K function essentially as a salt. The proof is in a universally composable model in this paper with Tash and Xiao. It's a strong opaque model, and the proof is generic, using any OPRF, any key exchange with KCI, with some properties of authenticated encryption, but everything that has efficient implementations. And if you use it with Diffie-Hellman OPRF, then the security is in the random oracle model under the one more Diffie-Hellman assumption. The protocol is forward secure, which is very important for password protocols, because if the password leaks, you still want the security of the session keys that you exchanged. And one thing that I didn't mention is that this can also support user-side hardening. So if you want to do hash iterations or use a function like a script or Aragon 2 now, these kind of functions, this is offloaded to the user, and that strengthens more the protocol against dictionary attacks in the case of server compromise. There's some nice extensions to the protocol. One of them, which is quite obvious, is credential retrieval. Since we already have this envelope that the user deposits at the server, then that same envelope can contain whatever secrets you are interested in, or any information that the user needs to have authenticated. So that's immediate from the protocol. Another thing that is interesting is that you can have a multi-server implementation where instead of implementing an OPRF, you implement a threshold OPRF, and it gives you the property that in order to break the system, the attacker needs to break into a threshold of servers, let's say 3 out of 5, 2 out of 3, 2 out of 2, whatever is your design. And even if it breaks, then it still has to do a offline dictionary attack. So this is a very strong strong model, and I think people should use it more in practice. Anyway, Opaque is very friendly to this implementation. And this requires changing the server side. It doesn't require any change on the user or client side. To summarize, so Opaque is modular and flexible. It allows composition of different protocols with different efficiency measures. You can do it pre-quantum, post-quantum, everything. All combinations are possible because the proof is generic. We've seen that there are efficient instantiations. Its integration with TLS is relatively easy. Nothing is too easy when it comes to TLS, but relatively easy. And very importantly, it gives a much more secure alternative to our current practice of encrypting passwords over TLS. And you can even have this hedging property of protecting TLS with password and not the other way around. Extensions, I mentioned credential retrieval and user transparent multi-server implementation. As for security, the protocol is secure against pre-computation attacks. Actually, it's the first true APEC in that sense. Previous protocols were not secure in that strong sense. Password is never in the clear outside the client domain. There's no reliance on PKI. We get forward security, client-side hardening, and a proof of all these properties in a strong UC security model. And to finish, basically, the reason I wanted to present this here is because I want to advertise this or give awareness to the possibility of standardizing on something like this. I think that if we are interested to standardize on a protocol that is better than what we have today, this is a very good candidate to do so. And the idea will be working on the CFRG and TLS working group for this, and any help will be welcome. So thank you, and here are two bit.ly links to the paper and the draft. And a word of advertisement, I didn't mention anything about other ways of protecting passwords that are complementary to Opaque, and it is using random independent passwords. Of course, that's not humanly possible, but you can do that with password managers. If you want to build a password manager, the best idea I have is this paper, Sphinx, that I presented actually 2 years ago. But I wanted to take the opportunity to remind people about this and see more use of this kind of stuff, which uses exactly the same technology, the same OPRFs as Opaque uses. Thank you.
Here we have time for one very quick question, and then we can. Sorry, Eric. And can the next speaker come up as well?
Hugo, can you wind back to the specification you had? I have a quick question.
How quick is it? It's already taking a while.
It's super quick. Super quick. So it may only be a technicality, but maybe the slide before where you have the OPRF. So you define the OPRF as applying a hash twice, if you look at the top line. But then in the protocol itself, the client learns more than that. It learns the actual Diffie-Hellman value. So it seems like there's a bit of a mismatch there. Maybe that's just a presentational thing.
No. The hash has to be the word. When I explained it, I ignored this external hash because the idea doesn't use that. But yeah, you need that external hash for security, and the point is that hash basically protects the key that is being output and is not protected from the client, which actually is going to learn the key, but is protected from the rest of the world.
Yeah.
So it is necessary in the...
Okay.
All right, yes. Why don't we just thank Hugo again and keep going. Thank you.
One, two, three. Is it okay?
All right, now we'll learn how not to share passwords, hopefully, if we have more than blank slides.
Let's see.
All right, great.
Yeah.
Take it away.
All right. Okay, thank you. This is a joint work together with Moni Nor and Benny Pincus. As we said, we want to learn how to not share a password. So, a second. Yay, it's working. Okay, so password has been around for a really long time. It's been known to be used in the Roman Empire days and probably even before that. But the first really modern use was probably in MIT's CTSS, which was a time-sharing operating system. And since then, it's been used quite a lot and causing quite a lot of damage. And due to that, people always want to kill passwords. And they've been talking about the death of password for many, many years and many, many times. However, as was previously mentioned, passwords are not dead yet, and are probably more ubiquitous than ever right now. And one of the many problems of passwords is that users tend to choose really bad passwords, many passwords with very low mean entropy, which are very easy to guess. Okay, so this problem has been around for a really long time. You can ask what is new about it. And what I want to say is that there is a change in what happens when people use bad passwords. In the past, if someone would have used a bad password, then you could read his emails and compromise its privacy. But today, bad passwords have a much worse meaning than that. They can actually try to compromise the entire ecosystem. They can be used for large-scale attacks. Maybe the most well-known example was the Mirai attack, which default passwords were used to create a very, very large botnet and create the biggest DDoS attack in history. And today it's really easy to find this kind of IoT devices on the web. And the main point here is that if someone uses a really weak password, like if I choose my kids' birthdays, then it might be bad for me. It will be easy to guess it, but it won't compromise the ecosystem because this password will probably not be very popular. But if someone chooses a popular password, let's say 1234 or password, then this is something that can really be bad. This is something that many users are going to use, and then it's easy to try to take over a large percentage of the devices. Okay, and there is a question that might arise. Whose fault is it? Is it the users that choose those bad passwords, or is it the server providers or the manufacturers that doesn't give them the infrastructure to actually choose good passwords? And recently, in this state of California, a bill was passed that says that this is we're going to move the liability to the manufacturers, to the service providers, and we're going to require them to do something about these passwords. Mainly, they must force the users to either use a pre-programmed unique password, which is something that users tend to really, really hate, or they're going to cause the users to choose a new password before they start using this device. However, the main question is, what password are these users going to choose? And we're talking about the same users that wouldn't bother to change default passwords, and they're not very security aware. So there's a large probability they're still going to use 1, 2, 3, 4 password because they don't really care. Okay. So what are the solutions? We need to give some guidelines to the users to how to choose a password. But this is something that's very, very hard. I'm sure that everybody here are aware of those pesky NIST guidelines that says you must have a number in your password or a capital letter or a symbol or something like that. And fortunately, a few months ago, NIST decided this is a bad idea, and they actually revoked those requirements and said, just ask the users to choose the longest password they're willing to do, and let's hope for the best. Because actually, nobody really knows what to do about this. Okay, so let's try to find other solutions. So there is the two-factor authentication that might be able to solve everything. Unfortunately, this is not something that really works in reality. I'm not going to go to the details. There's a very good blog post just a month ago from Ilya from Google saying that actually two-factor authentication is not something that's used too much in practice, which is unfortunate. Okay, so let's do another thing. Let's force the server to simply store all of the user's password. Then it will gather a good statistics and see if there are any popular passwords, and then it will just blacklist those popular passwords. And I think that for this audience, I don't really need to explain why this is a really, really bad solution, and we don't want to do this. So how can we blacklist those popular passwords? Maybe we'll just blacklist what we know to be popular password. There is some knowledge from previous data breaches and some common knowledge that, I don't know, came out of the air. I think everybody here knows that 1234 is a popular password, and password is popular password. I'm not sure if you know that Superman is a very popular password, and there are some others, but okay, we know. So let's just blacklist them. And I want to claim that this is not good enough, because password distribution might change over time. We'll give one example. People wanted to use password, and then NIST came in and said, no, you have to add numbers. So they changed the O to 0, and then they add the symbol. But now they don't need to do it anymore, so they go back to password. This is changes that we want to be able to follow. Superman, as I said, was a very popular password. But due to recent cultural changes, we might presume that Wonder Woman is going to be much more popular in the near future. We also have different populations in the world. There are people with different ages, speaking different languages, and they probably choose different distribution of passwords. And moreover, there might be some very weird stuff that just pops out into the world, and we want to be able to find this kind of thing and actually block them. Okay, so the first thing we want to do, we don't want to cause any harm to the world. We are good people. We want to use cryptography for the common good. And actually publishing those blacklist of passwords might really help attackers. Okay, now they know which passwords are popular, and they're going to try them. So first thing, we say this is their day job. Attackers already know what the popular passwords are. We want to help the people that want to defend us. And more importantly, we think that publishing a blacklist is pretty much like publishing some code vulnerability. We're going to notify the public. We're going to say, you need to stop using those passwords, or you need to update your software. And if the people are not doing this, then okay, they might still be vulnerable, but we're going to help to protect the entire ecosystem, which is important enough. Another point that we need to realize is that leaking any information about user password is something that might hurt the users, hurt their privacy. And to gather some statistic out for password, we need to learn something about individual users' password, some kind of information. So the first thing we want to claim, and we're going to try to prove it, is that 1 bit of leakage on password is not something that's really going to hurt the users too much. And moreover, we can show how to use differential privacy to also help and reduce the amount of leakage on user password to something that can really preserve their privacy. So we first want to define something called the password game. In the password game, we have an attacker that wants to attack some device. And the attacker is going to publish a list of link L of the L passwords, and this is its guess for the password. And it's going to win if one of if the password of D is one of those in the list. So we can easily show that the effect of 1-bit leakage is at most that the attacker needs to do 2 times as much work or 2 times as much password guesses. So it doesn't help the attacker very much. We also have a similar property for differential privacy that we show that if we protect with differential privacy the leakage, then the attacker can't improve his probability of success by much. Okay, so what we actually want to do after that we're satisfied that this is okay, we want to be able to identify and blacklist popular passwords, what we call heavy hitters. And those are the passwords that are chosen by some fraction tau of the users or more. And the server should not learn more than 1 bit of information on any of the user's password. And this at most helps the number of password guesses. And one thing that's important to us, we want the probability of false negative to be negligible. That means we're not going to miss any of the popular passwords. We want to catch them all. However, we can afford to have a small non-negligible probability of false positive, which means a legitimate password that the users want to choose might be rejected with a low probability, as long as it doesn't happen too much. We don't want to annoy our users. There is quite a lot of previous work in this field of finding heavy hitters with differential privacy and also trying to find popular passwords. We think that our work is a little bit different. And the main thing is that we are very, very pessimistic people. We think that the world is a malicious world. And in this world, both the users and the server might be malicious. And most of the other work are in the semi-honest model. And a malicious server is a relatively simple creature. All it wants to do is to learn as much as possible about the user's password. However, the malicious user is something that is a little bit more complex. And the malicious user basically will want to hide popular passwords that are trending. If an adversary already controls a large coalition of the user, you want to hide this trending of popular passwords so the server won't blacklist it, and as much users as possible we're going to choose them. Okay, so what we have here is basically what we call MPC meets differential privacy in a malicious world. And we have an asymmetrical requirement for the security of the protocol. And it's basically relatively easy to protect the user's privacy from the server. However, it's much harder to protect against colluding malicious users. And I'm going to try to give a simple example. Let's say I want to learn what is the approval rating for Trump in this room. So I'm going to ask all of you to vote if you support Trump, but I want to protect your privacy. So I will tell you that with probability 1/3, you're going to flip your vote. And this is proven to provide differential privacy, and everything is good. However, let's say the Trump supporters want to increase his approval rating. They will try to cheat, and they will not flip their vote. They will always vote for Trump. This will cause his approval rating to be much higher than it actually is. So we need to have some kind of two-party computation in order to protect the correctness of the results. And we have some that is tailored to the requirement that we have. So if we want to try to at least semi-formally define the correctness, is that we want to be able to detect as a heavy hitter any password that is used by more than 1 plus delta tau fraction of the users. And this is even in the presence of this malicious user coalition. And we want to not identify passwords that are not popular, which is they are less than 1 minus delta tau fraction of the users, with a relatively high probability. So we have this example of a blacklist. And actually, we have that the upper red line is 1 plus delta tau. We want to be able to identify all of the passwords that are more popular than that. We want to not identify any password that is under the green line. And anything in the middle, we don't care. We can go either way. OK, so we have a semi-honest solution for this problem. And it's very similar to the one by Basili et al. And in this, we do a kind of domain reduction. We hash the password into L-bit hash values. L might be 16 or 32. And we're going to actually ban all of the passwords that will hash into these hash values, into popular hash values. And again, we might have a small probability for collision, where a not popular password will collide with the hash of a popular password. But this is OK as long as it happens with low probability. So the server is going to save a counter histogram with size 2 to the L, and it's going to initialize it with 0. And the protocol is very simple. It looks like this. The server will choose a random L-bit value for each user. It will send it to the user. The user will hash its password and calculate the inner product of the password with this L-bit value, and will send the 1-bit result to the server. The server is going to iterate over all of the possible values. It's not so much, so it can be relatively fast. And if the inner product of any hash value is correlated to the one that was sent by the user, it will increase the counter by 1. Otherwise, it will decrease the counter by 1. Which basically means that for the specific hash that the user chose, the counter will always be increased by 1. For any other hash value, the counter is going to, in expected, remain the same. So we'll have an example here. This is a toy example with L equals to 3. And let's assume that everybody wants to choose the hash value 5. So they start to run the protocol with the first user, the second user. Each time the value of 5 is increased by 1, and the other values are doing this kind of random walk. So after 10 users, we can see that the value of 5 is very high. The rest of them are much lower, and we can identify this value. And we can actually show that the expected value of each counter is what we want to learn. We blacklist any value that is larger than tau n. N is the number of users. And we're going to dynamically choose tau to be large enough so that this random noise that we get from the random walk will not break the correctness requirements that we have. OK, so this sounds perfect. It's relatively simple. But we have a problem, because we live in a malicious world, and we have what we call the undercount attack. In this attack, an attacker wants to hide this popular password and the popular hash value. And the attack is very simple. He will just follow the protocol by choosing this password, and will flip the bit of the result. And we can see what is the effect. Let's say we have the current situation. There are 10 users that already voted for 5, and now there are users trying to undercount. And we simply remove the value until we can get 0 in 5, and the password is not identified, which is bad. OK, so now we want something that's in multi-party computation. We have the trusted third party. This is the ideal world. In this ideal world, the user will send the hash of the password to this trusted third party. The server will send the random L-bit string, and the trusted third party will do the inner product calculation and send the result to the server. The user doesn't know R. It doesn't know the result of the inner product, so it can't cheat. And the server doesn't learn anything about the password. OK. So we actually have two approaches of how to implement it. One is based on quadratic residosity assumption, and the other is on Yau's garbled circuit based. And we try to show the naive QR-based solution. And again, it's based on the interactability of quadratic residosity assumption. And what we're going to do is we're going to encrypt this L-bits in Goldwasser-Mikali public encryption. And what we're going to do is encrypt 0 as a quadratic residue number and 1 as a non-quadratic residue number. And the server is going to generate a RSA modulo for each user. We'll encrypt its bits. And what the user is doing is very simple. It will just multiply all of the encrypted values that correspond to 1 values in the hash, and we'll blind this with some random number and send it to the server. The details doesn't really matter, but the main point here is that the user can't learn anything about the R value. So does it mean it can cheat? And unfortunately for us, the answer is no, it can't cheat. And if he is able to create a number which he knows with high probability is not a quadratic residue number. And so we have the NQR generation assumption. We ask, is it hard to find such numbers? And we go to the scriptures for the original Goldwasser-Mikali paper, and they actually say there they don't know. And unfortunately for us, this is an unsolved problem. We have a simple reduction for the security of the protocol, but we were not bold enough to use this kind of assumption that's not proven. So what we actually do is we're going to use interactive zero-knowledge proof that a user can prove to the server that he actually did the inner product calculation as it was intended to be done. We also have a non-interactive version but based on the Fiat-Shamir heuristic, which is something that's very nice because it simplifies the protocol and make it very easy to change your password. It's also required a proof, some other proofs, so that the details don't really matter here. And again, we have the solution based on garbled circuit. What is basically maybe more important is what is the bound on tau that we can identify, which means what is the least popular password that we can identify in a blacklist. And this is a function of the number of users. If there are more users, then we can find passwords that are less and less popular. And what we did was to check against known data breaches, and we can actually say that we can blacklist the top 3 passwords that were leaked in the Yahoo leak and the 5 top passwords from the RockU leak. So we feel that this can be actually used in practice. To make sure that this can actually be used in practice, and we're talking about maybe IoT devices, which are very low resource, we implemented the full malicious QR protocol on a Raspberry Pi, which is a relatively low resource device. And in it, this very inefficient implementation, it takes about 50 seconds to do the entire non-interactive calculation. Remember, again, this is only done when the user changes his password, and it can be run in the background. So we think that's actually plausible. For a server, and by saying a server, I mean this laptop, it takes about half a second to verify the entire process. We also feel that this same solution can be used in other places where we want to gather statistics in what we think is a malicious environment. For example, let's say that some government wants to cause people to stop using the Tor network or stop helping it. So they want to prove that Tor network is only used for drug trafficking. So it's going to try to influence the statistics of what IP addresses the Tor network access to show this kind of result. So we want to maybe try to protect this kind of statistics. We can also use it in maybe trying to find out what are the popular device spin or patterns for smartphones, and help a large service provider to be able to learn the password distribution over their entire user base or over the distinct populations. Okay, we have some, what we think at least are very interesting open questions. From the cryptographic side, the first one we want to know is, do we need crypto? We know that for the semi-honest solution, we don't need any kind of crypto to do this solution. But in the malicious world, we use quite heavy crypto machinery. We don't know if, we can't prove so far that it's needed, although we think it is. We will have to see some more research on the NQR assumption that we described here, because it will help to simplify our protocol. And in the more real-world stuff, and then a very important question is, can we prove the bounds that we have on tau? We want to be able to identify passwords that are used by as little part of the population as possible, and blacklist it. And the main reason that was important for me to talk here today, we want to try to have real-world implementations of this protocol on real passwords and try to see if we can get any nice results out of it. That's it. If you have a more question, we'll be able to answer, and more information can be seen on the full paper or on my website. Thank you.
We have time for one quick question, or we can cut to break, the aforementioned elusive break. All right, why don't we just do that? So let's thank the speaker again. Thank you very much. And we'll be back 10 minutes after the top of the hour.
Make sure there are no questions.
No one was getting up anyway.
So, because I understand, but don't I supply my password hash now to the central server?
No, it's masked, I think.
Is it masked? It doesn't be masked. Otherwise, like, if I have a low entry password, but I think I have a high entry password, it's real tough, right?
Okay.
Everybody else choose 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you know?
Well, if they're only able to block the machine learning.
That's a good point, yeah.
We've got a team that's sort of doing that stuff now. So you can do
I gotta find Dan. Like, Priya, because I know Priya, they've been also heavy hitters. Yeah, exactly, yeah. We're starting to look at doing Priya, actually. Pretty seriously.
Yeah, Henry was mentioning that.
gotta get it. Yeah, absolutely. Yeah. Because like we had a lot of problems. We were like, gotta dig out the data. So we deployed it. For collecting data we already had, and now we're looking at collecting data we don't. Gotcha. So first, I want to make sure like gives the right answer. Our fault, not theirs.
I'll find out next time, but let me go deal with this because I made a promise.
Code gets fed into the code gets fed into the like sometimes it's a big problem that they have tonight. And it's like no data. And like yeah, so like art is like fully our fault.
Anyway, fine, Dan. Yeah.
So you might want to plug in and do a quick test and see. Hey, how's it going? And you guys are joining the testing, aren't you? So one of you probably wants to use this, and then the other that one. Yeah, you're working out between you. Okay. Hi, I'm Kenny. I think I saw you told us that you used the SSS in the session. No, I don't know. Okay, it wasn't you. Maybe I saw your name.
Yes, my name was on my student list.
That's what it was. So we'll do a test and see how this thing. I'm not sure you're in your session check. I think it might be touch. But
Extended. I don't know.
let's check. Yeah. So, do you know him?
I've emailed with him, but I don't know what to look at. Oh, there we go. That looks right now. Ha 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 ha. How's yes, we're good. Okay. Okay, we're good.
You guys have a pretty short, slot.
Yeah.
So you've been rehearsing?
Yeah. Yeah. We'll definitely, we might go into the Q&A if I
That's fine.
Okay. Yeah, we're definitely.
That just means you get less, Q.
Okay. Yeah. We'll definitely. We might have like 4 minutes for questions, but we'll definitely be within our time.
Some people aren't really leaving themselves any time.
Yeah.
It's a friendly crowd, so if they want to ask you questions later, they'll catch up with you. Great. Good luck with it.
Yeah, awesome. Yeah, thanks for the opportunity.
And mine is 35 minutes including the Q&A, right?
You're in longer.
Yes.
I think the intention is 30 plus 5.
30 plus 5, okay.
For Q&A.
Perfect.
And I'm sure your talk's going to provoke some Q&A.
I'm sure. I have comments. I usually do. Okay. Let's see. Alright, so I see all of the things, yes, but where's the other end? Yes, that's what I was wondering.
Folks dropped it. There you go.
There we go. I was like, good to have it, but gotta know what it connects to. Okay.
Is this your first RWC?
It is.
Okay. What do you make of it so far?
Oh, very cool. I especially loved the politics session this
That was
morning.
good, wasn't
I was
it?
a big fan, yes.
Yeah, you're up in display. So.
Oh.
It's lovely when it works, huh?
Isn't it? I would
Yeah,
like
that was
to
lovely.
not mirror
Both
it.
talks in that session were great, actually.
Yes, I enjoyed that tremendously. And let's just make sure I can get my presenter view.
That's interesting, isn't it?
Don't do that. Thank you. All right, gonna have to fix that. Okay, that looks good.
Yeah? Happy?
Yeah.
Oh yeah, now you've got your next slide feeding
Yep,
everything,
that's
right? Yeah, I like that.
Yes,
really
I
good.
like that too.
Okay, good.
Nothing else to show up on that side. Okay.
All set?
Awesome. Thank you.
Thank you.
up here? You need to mic up, I guess.
Yes. And I also
Oops. Mic yourself up. It's you. I don't know if we have an AV person or not.
Wait a second, it was working.
Do I need to run somebody down?
I didn't know if you wanted it.
Hello? 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 Can people hear me? Hello? Hello, welcome back. Hopefully you're all sufficiently caffeinated for the last session of the day. Dan just let me know that 2 garage tickets have been found. If you know what a garage ticket is, you might want to check your pocket to see if you've lost yours. 2 garage tickets have been found and they are at the registration desk if you're missing your garage ticket. We've seen some excellent talks today, and I have no doubt that our last 3 speakers will continue that trend. No pressure. And the first speaker of the last session today is Josh Barron from DARPA. Josh.
All right. Hi, everyone. Why not? Hi, I'm Josh. I'm a program manager at DARPA. I've been there for about 1.5 years. And today I want to talk to you about DARPA's investments in real-world cryptography. I don't know. That's as creative as I could really get with this title. So let's talk about the research that DARPA has been doing in crypto. So in the beginning, there was Proceed, which was really about computation on encrypted information, largely focusing on fully homomorphic encryption, also looking at MPC, secure multi-party computation. Then there was Safer, which was looking mainly at kind of resilient comms on the internet. Some of the pluggable transport work came out of that for Tor. Again, pluggable transports, decoy routing, and then actually even low-party MPC. There was some work done there. Then there was Brandeis, which was looking at building privacy-aware systems. The focus there is a little different, so not just MPC, but also differential privacy and human factors. There's also Safeware, looking to do something called indistinguishability obfuscation, which is anyhow, we'll leave it there. And then Race, which is doing secure distributed messaging in contested network environments, largely focusing on MPC and obfuscated communications. And then the question is kind of where are we going? So today I'm going to talk about, frankly, I'm going to talk about those things for which I'm responsible for. So I am the program manager for Brandeis. I'm the program manager for Race. Just in case you're kind of unaware of those terms, what that means is I do nothing. I just pay people to do things. So all the really cool things are done by the folks in this room. Yeah, OK. So let's talk a little bit about Brandeis. The idea for Brandeis is, typically speaking, if you really want to secure your data, you encrypt it. But then when you encrypt it, you can't really do anything with it. But then when you decrypt it to do things with it, then of course it's vulnerable. So like, how can you have your cake and eat it too? And because this is really about privacy, I should also mention that part of the focus also is having the level, it's not just a confidentiality program. How can I have the security that I want, no more, no less, right? So if I want to play Angry Birds, I know that it's going to sell my location to people, but that's what I want to do. OK, fine, you get to do that. OK. So the way that we're structured, think of it as, we have a data owner. We're focusing a lot on kind of this human data interaction. How do I best communicate about what I want? So my favorite example on this is I had a lot of friends who wouldn't download Signal on Android because it said that it wanted, and especially initially, because it said that it wanted all your contacts. And they're like, well, these are privacy, aware people. And like, I don't want to give you my contacts. And of course, the reason that Signal wants that is so that it can easily say who of your friends are using Signal, who your contacts are. But that communication was left out. So wouldn't it be better if when you're popped up with do you want to give an application this or that privilege, it actually told you in an efficient manner, in a decision that you can make in like 3 seconds or 1 second, why it wanted what it wanted. So that's actually some of the work we're funding under Brandeis. I'm actually not going to be talking about any of that today because we're about crypto, and so actually Michelle, who's fantastic, will be speaking most likely about that, but fine. We're also on the flip, we're doing a lot of privacy preserving technologies, which you kind of see in those orange squares. That's largely secure multi-party computation and differential privacy. And then we're kind of wrapping that all into these TA3 integrators. So roughly speaking, what we're doing is we're taking 3 application areas, namely smart buildings, coalition information sharing, and mobile phone application stuff. And we're specifically trying to push these kind of prototype privacy-aware systems in those areas, and we'll talk more about that. And finally, and frankly the hardest, we're trying to measure privacy. And that's actually super hard, mainly because it's not entirely clear what we mean by privacy, so it's kind of hard to measure that, among other things. Alrighty, so here's one thing that we're doing, and again, it's not, this isn't crypto, but I just think it's super cool. So one of the things that we're actually doing is we're developing a set of extensions and additional interfaces that are built on top of and into the Android OS, which is actually roughly similar to how Google Play and SE for Android work, if you're familiar with that. And we're actually at a pretty current state. So we actually have this running, I think, on a phone on Android Oreo 8.1 right now. And so what this does is it's a principled separation between among other things, a principled separation between applications and your underlying private data via these PALs, or privacy assurance locations, or something on that order. And of course, you need to abstract some of the really technical ways we're doing this away from the people who need to use these things. And there's a bunch of human factors elements baked in. So the example, that discussion about locations and stuff like that, or why you need contacts, we're actually baking into the OS. It's super exciting work, and I really hope it ends up going somewhere. So that's kind of fun. Beyond that, in terms of what I want to talk about Brandeis, I'm going to focus specifically on some of the MPC work that we're doing. When I took over Brandeis, I kind of took it over midway. And kind of the thesis for me is that, and I don't know if this is either going to be super controversial or not even remotely controversial. Roughly speaking, I believe that MPC is completely practical for some applications. And it just kind of confuses me why it's not used. And for some of you, again, you might be nodding your heads, and for some of you, it'd be like, that's completely crazy, but that's kind of where I'm coming from. And so what I've been trying to do under Brandeis is actually show some very specific applications that are completely efficient now using MPC. So here's one specific example. Here you see a map of Boston. There are aid stations, and then you have an ailment, and you kind of pick one of your ailments, and depending on that ailment, it routes you to the aid station. And this is kind of relatively intuitive. This is, I think, like a year old in terms of what we have. The catch is that this is actually done via encryption, which is to say that the underlying, the status and the capabilities of the aid stations are encrypted at all times. The actual ailment that you have is also encrypted. It just routes you, it figures out that route and where you're going and why, again, purely by computing on information while it remains encrypted. And this has a number of applications, right? So don't just think of it in terms of how do I get to an aid station, but all kinds of other resource allocation, as it were, solutions that I think, especially in the low party, relatively low complexity cases, can be done basically now via homomorphic encryption, partially homomorphic encryption, and secure multi-party computation. Another one that I'm also really excited about is, we're doing a lot of work in the coalition information sharing environment on disaster relief, humanitarian aid and disaster relief. So suppose I have 10 countries with like 26 ships, and I want to route them to 10 different ports to give aid. But the thing is that I really don't want to say where my ship is. I really don't want to say what its speed is, what its displacement is. So could I upload all of that stuff encrypted, and then what pops out is show up at this part of the port at this time, right? So we're doing that right now, completely unoptimized in about 7 seconds. So again, this is, and what you can think again is this is kind of a somewhat basic resource allocation question on encrypted information. And again, I think in this case, it's really quite doable. It looks something like this. Underlying, so this is some of the stuff that we're supporting. Scale Mamba, which is some fantastic work you're going to be hearing about later. Garbled RAM, Oblivious RAM, SGX, and just in case SGX isn't secure, We're also supporting Sanctum, which is some amazing open source work, SGX type thing. I think that Srini will be talking about later. Functional secret sharing. So one of the cool things there is we can, so for those familiar with secret share databases, we can upload, so if you have a two-party sharing of a secret share database, and these things could be vast. So how do you update the secret share database and not have to do a secret sharing for every single element in that database? So we can do that with like a couple of AES encryptions. So uploading a giant secret share database in like nanoseconds. I'm not talking about it, but I just want to mention some of the work we're doing in differential privacy is incredibly exciting. That first one actually is going to be, basically talks about if you have to ask a couple of complex questions and want to balance your underlying privacy and what you're giving away. The census will most likely be using this for the 2020 census, so I'm really excited about that work. And then some other stuff, which I don't think I have time to talk about. So I want to talk briefly about race, resilient anonymous communication for everyone. So the idea here is to use, so let's just talk about the problem. The problem is Tor is amazing. That's not a problem, that's a fact. The challenge with something like Tor is that the way it has to work is it has to be distributed, right? And it gets a lot of its resilience from being distributed. But when it's distributed, it basically has to announce where it lives. And because it announces where it lives, it's blockable in what we will call contested network environments. You can think about where. So the idea is, how do I build a distributed system that knows enough to be distributed but doesn't know enough about itself that it's targetable, right? And so what RACE is trying to do is trying to solve that essentially using secure multi-party computation as well as hidden communication. So if all it did was MPC, that would be like, cool story, you're running really weird crypto in a distributed fashion, I'm just going to block all of you. So you have to do both the kind of the MPC part as well as we're funding a good amount of work in how do you hide communications better. And this work will be kicking off in March or April is the hope. And the security guarantees are actually pretty strong. Notably, it's not just about hiding your messages. It's not just about hiding your metadata, which is also important. It's really also about, I'd really love it to be unobservable, which is to say, if I am not sitting on a system running this thing, you shouldn't be able to infer that it's actually running it. And just to be, because I probably haven't said it, it's a mobile application with a distributed backend. So that's basically what we're doing. I get that there are a lot of mobile messaging applications out there. The goal of RACE is not to develop our own messaging application. That's the most magic thing ever. Quite frankly, my goal is to open source all of the libraries associated with it and release it to all of you to do really cool things with it. Right? So this is a completely open, our goal is to be as open as possible, to develop all this open source, to give it out, and then hopefully some of those really great secure messaging applications could implement this in some really hard to reach places. Okay, I'm not going to talk about that or that. So what's the future? Why not? So I want to talk about two things briefly. One is zero knowledge. It's interesting to me that no one in DARPA or IARPA has ever done anything in zero knowledge. Zero knowledge is the ability to prove to you something without actually telling you, the underlying secret. That seems like a canonical DoD kind of thing, and yet we really haven't chased it. I think with one of the things that the cryptocurrency community has demonstrated is really the efficiency of relatively low complexity zero knowledge statements. So my question is, what happens when I take really complicated zero knowledge statements? So things like reasoning about the security of software, or reasoning about the insecurity of software, or other kinds of interesting, very complicated statements. How far can I push that and still have a somewhat, like computable in a day kind of zero knowledge proof? I think that's kind of interesting personally. I'd be curious to hear your thoughts. And then finally, consensus protocols. Some might call that blockchain. So we released a recent RFI about applications and barriers to consensus protocols. This is kind of me poking at consensus protocols to see how relevant I think they are for the Department of Defense. So one is like, what can we really do now that we can't do before? From that perspective, permission blockchains are distributed computing from the 80s. I'm not saying they're not cool. I'm not saying you can't do cool things with them. I'm just saying, fighting words, I don't think they're new. I think permissionless is really kind of where it's at. And that's the thing that was really not possible before, developing these highly, highly distributed consensus protocols. So what can we really do with them? I think one of the things that Bitcoin showed was that economic analysis plus computer security means very new things. So the idea that it's suddenly not secure or insecure, but I'm bribing you to do something, and that means that you're not necessarily good or bad, you're just getting paid. How can we take that and build better models of permissionless distributed consensus protocols? The other question, quite honestly, is how secure are these consensus protocols really? It's interesting to me that people talk about consensus protocols as they're secure because they're distributed. That's kind of like saying my computer is unhackable because it can do AES. It's not like there are different levels of abstraction. And so when we think about consensus protocols as actual distributed systems, my question is, what's the underlying security of that system? Because we know that in some ways, some of these protocols are central. There are papers, and I know there have been kind of defenses, but talking about at the AES level, Bitcoin is actually rather centralized. Or supposing that if everyone using your giant distributed consensus protocol is running the exact same software or developed by the same 5 people, that's a centrality. So how do we think about those centralities? How do we defend against those centralities? I think that would be interesting. So thank you. That's my time.
So we have time for one question. Maybe somebody wants to come and disagree with Josh about MVC blockchain. Do we have one? Yeah.
Hi. So Philip Roggeway in the moral character of cryptographic work spoke against DARPA and accepting funding from it. And he wrote, quote, "The military funding of science invariably redirects it and creates moral hazards. And think twice and then again about accepting military funding. What do you have to say about that?"
I think academics are absolutely free to make their own decisions. I think the things that we're developing are important, and I think it is completely up to an individual academic whether they want to engage with us. I think that's completely fair.
Excellent answer. Where are my next speakers? Both of them. So while we're waiting for them to set up, I'll remind you all that we have a reception tonight at 5:30. I'm not exactly sure. Wait, Nigel's motioning to me. Did you have something you want to say? Are you sure? You always want to talk. Oh, okay. There's a reception at 5:30. Do you know where it is? Apparently no one in the steering committee knows where it is. It's someplace and we'll be at 5:30. Are we ready? Are you guys mic'd up? Or do you want this mic?
I'm going to take that mic.
Okay, well, in a moment. Okay. So happy to introduce our second talk of the session, completely switching topics, looking at when theory meets practice for journalists working with encrypted documents, and we have a joint presentation by both the authors, so I'll just pass this on.
Thank you. All right, so can't hear you. As was said, what we're going to be talking about.
You have the mic that works.
Keep speaking. Okay, I'm just saying random words.
Again?
Hello?
That works.
All right, very good. So, as was said, we're going to be talking to you today about when theory meets practice for journalists working with encrypted documents. And specifically, what we're going to be looking at is the use of threshold schemes in this setting. So, for the majority of this talk, we're going to be working with a specific example just to kind of facilitate the communication of it, where there are 3 participants within the scheme, and it requires at least 2 of them to cooperate in order to recover their secret information. So, each participant is given some information that is not the entirety of the secret, and on their own, they are now no longer able to recover it by themselves, and as a pair, they can for any pair within the scheme. So if we talk about this within the sense of a journalist who has been entrusted with a sensitive document and they want to store it in a secure way, perhaps encrypted on some device, if that device is compromised or destroyed, then the document itself can also be eliminated. So there's this single point of failure if you want to prevent the distribution of this information. If we instead move to a threshold scheme, we can have some level of redundancy added in, and even if one of the participants in this 2-3 setting loses their device that had their information necessary to recover the sensitive data, there still remains 2 others, and the secret information can be recovered and then distributed at the appropriate time to the public. We also, through using a threshold scheme, are able to
achieve a level of distribution of trust. So no one person, assuming your threshold is greater than 1, is able to make a unilateral decision about distributing this information. So if you're working with information that should be carefully processed, you're able to ensure that there's some oversight by having some consensus required for distribution. So recently, Freedom of the Press Foundation came out with an alpha release of the tool Sunder, which is a graphical interface that enables the users for a secret that they possess to choose their desired threshold and their number of participants, and then proceed to produce sufficient shares that they can then recover the secret at will. So we're going to work with Sunder a bit as a case study to facilitate our talk of how to use threshold schemes in a more practical setting. So looking at a basic kind of approach and a high level of the protocol, you're going to have the person who has been entrusted with this information, who is the dealer, who chooses the appropriate threshold and number of participants depending on the threat models they're facing and the level of redundancy and distribution of trust that they want. They can then feed this information into a tool such as Sunder that can perform the secret sharing for them. In the case of Sunder, it uses a Shamir threshold scheme, and the good news is that you can have any desired threshold you want, as long as the threshold is less than or equal to the number of participants within the scheme. So once you put it through the tool, you get to the desired shares as output, and then the dealer will keep one for themselves and distribute the remaining shares out to the other participants they've selected to be valid for providing consensus as to when to distribute this information. We have a second phase of reconstruction, which is simply the threshold number of participants recombines and are able to recover the secret by inputting their shares through the tool. Now this works quite nicely if your secret you're dealing with is only a few megabytes, but perhaps if you're working with larger data, you might want to consider an extended setting where instead of just sharing the sensitive information itself, you generate a key to serve as the secret, which you can then use for an appropriate encryption algorithm to encrypt your plain text sensitive information and produce the ciphertext before proceeding as normal and distributing the shares to your desired participants. The reconstruction stage changes similarly, with just adding this extra step, because when you recover the secret, you no longer have that sensitive data until you apply your key and recover it like so. So what we wanted to focus on was considering the security of a complete threshold system, not just at the protocol level, but also out to like Ellison's term ceremony, which includes not just computers, but also the people interacting with the system. So if you talked about something like TLS, which is the protocol, outside of it, if you had something like a pop-up in the case of a bad certificate, the user's interaction and what they should appropriately do when seeing this pop-up would be something that's included in the ceremony and is relevant for TLS to actually be providing them with complete security. So what we're going to do is treat Sunder as a protocol, but we also have this external documentation that specifies the actions that are appropriate for the user to take. And what we're going to do is highlight both at the protocol level and the ceremony level, where in these protocols I've kind of outlined for you so far, there are gaps that can lead to security loss for people working with this information. So in the last half of this talk, what we're going to highlight for you is just a few of our select gaps that we picked out for you today, as well as the improvements that we have identified and are ongoing working on implementing.
Okay. Ooh. I don't think we should get too close to each other. Okay, so as Bailey mentioned, Sunder and secret sharing schemes are being used in practice by journalists. And so we're going to look at the gaps and some improvements that can be done in order to help them achieve their intended security guarantees. So one obvious potential gap is that of share loss. So in the base scheme, secret sharing schemes are really useful because you can lose up to a threshold number of shares. However, after you lose that threshold number of shares, the secret is no longer recoverable. And we know that humans are fallible, they lose things. So that's something we essentially like to improve. And attackers can also take advantage of this because they can destroy or they can perform a denial of service attack against these shares, which would also render the secret unrecoverable. So one way that we can improve upon this is by adding a repairability algorithm. And these are pretty well known in the literature. Essentially, what they allow you to do is if you have a threshold number of shares or more, you can recover shares which have been lost using the repairability algorithm. And we're not going to go too much into them right now. We wanted to cite some literature where you can find more information about them. But there are schemes which you can use immediately with Shamir today. So another gap that we identified is that of organizational turnover. So when you are going about sharing a secret, you might want to protect some kind of organizational secret. And at the beginning, everyone might be within the organization and everyone might be immediately trusted. However, what happens if one person goes and leaves the organization later and they take their share with them? So in this case, they're moving from a trusted state to an untrusted state. And in the current version of Shamir, that actually isn't protected against. And so this person who's moved from trusted to untrusted can continue to collude with someone who is potentially within the organization or maybe even people who have left. So there's no sort of differentiation between organizational confidentiality and protocol confidentiality. And so one way that we can improve upon that is by allowing dynamic updates within the shares. And so essentially, if someone who was trusted before then leaves the organization, the remaining number of people can perform an update on their shares such that those updated shares, only those together can recover the secret, but you can still recover the original secret. And this is something that we are currently doing an implementation of in Rust, and we will detail more in our upcoming paper. So now we're going to look at some gaps and improvements in the extended model. Okay, so one gap which is pretty simple to fix, but isn't defined in Shamir, is that of integrity. So when you share a secret, if the secret is the key to some ciphertext, that original key, you can be sure of the integrity of it via Shamir. However, it isn't actually defined about how you verify the integrity of that end ciphertext. And so one really easy way to improve upon this is by secret sharing some integrity value. So that might be a MAC or a signature. And so that in of itself can also be fed into the Shamir protocol and secret shared to the other participants. And so finally, we'll look at really quickly about redundancy. And so we talked about redundancy before. If you were to lose some shares, if you were to lose up to a threshold number of, if you were to retain a threshold number of shares, you can continue to recover the secret. So you can afford some loss there. However, in a tool, something like Sunder, there's actually no definition around how do you achieve redundancy with the end ciphertext. So that ciphertext could only be stored on the dealer's machine, and if that machine goes away, it doesn't matter whether or not you can recover that key, that ciphertext, your actual protected document, you can no longer recover. And so there's a lot of ways that you can go about fixing this. This is just one way that we identified, but surely there's other ways that this could be solved. But essentially, one easy way to fix this is you take that ciphertext and you copy it to several different servers of which you trust, and they're all sort of independently located. And that is just a cheap and easy way to ensure redundancy for that end ciphertext. So now we're just going to quickly look at some ongoing and future work. So as Bailey mentioned, right now we are doing a complete ceremony analysis, and our goal is to essentially look at what is the true end-to-end path for a user who is using a tool like Sunder, and what are the different kind of decisions that they need to make along the way. And so we want to define what that end-to-end path looks like in a secure manner. And also what we're working on is that updating shares functionality, so you can have some kind of dynamicism in the protocol without having to rerun the generation protocol all over again. And a few areas of future work that we identified. So repairing algorithms are really useful and they're well defined. So adding an implementation of them for lost shares would be useful to existing Shamir implementations. And then finally, a good area of research is designing schemes to limit the dealer trust. This isn't something we've gone into in great detail, but obviously there is a lot of trust placed in the dealer, and so how can we limit that and help provide some kind of buffer and safeguard in that case? So overall, what are some of the takeaways that we want to emphasize from this talk? One is that secret sharing schemes are not suitable for real-world use as is. Really, there needs to be additional things in place in order to fill the gaps to ensure integrity, confidentiality, authenticity, and availability. And finally, ceremony analysis helps identify the gaps between what's expected of users and the end security expectations that we have for the system. Thank you.
At this time, we just like to thank Freedom of the Press Foundation for talking to us about their different use cases, as well as thank Ian Goldberg for his feedback leading up to this presentation and his ongoing involvement in our upcoming paper. Thanks.
Thank you.
We have time for one question.
Hi. Is secure deletion a part of your use case? Being able to delete the data securely and have assurance that all copies are destroyed?
Yeah, so that is something we assumed within our mode of analysis. Ensuring secure deletion is a hard problem.
But you can't, so we have to some level assume there's some way for you to delete it, because otherwise there's currently that problem where all of that information is at one point on one device. And if you can't come up with some mechanism to reach some limit of deletion, you do have that one single point of failure where if someone's able to compromise it, they could learn all the information they want.
Thank you.
Thank you.
Okay, let's thank our speakers again, please. And while Michelle sets up, some of you weren't in the room when I announced at the beginning that 2 garage tickets have been found. And they are at the registration desk, yeah? Yes. And Kenny's making a drinking motion at me. Should I have a drink? Is it? You want us to go get drinks? I'm ready. Was there actually something? Drinks. Oh, I'm also supposed to remind you again that there's a reception at 5:30 that none of the three of us know where it is. You know where it is. It's just out here where we were meeting? Yeah, okay. So reception 5:30 out there. There we are. So to bring us home today, we have Michelle Mazurk, who's going to talk to us about mistakes that developers make. Michelle.
All right, how's that? Better? Okay. Hi, so as mentioned, I'm Michelle. I'm an assistant professor at the University of Maryland, and I'm going to talk to you about some work we've been doing trying to understand security mistakes that developers make. So many real-world vulnerabilities arise from quote-unquote solved problems. So I'm using solved extremely advisedly here, right? Obviously they're not solved because they still exist in many cases, but these are things that we at least, on some level understand the technical solution to. This graph is from the NIST National Vulnerability Database showing like the prevalence of buffer overflow related vulnerabilities over the past 20 years or so. And we can see that, these, even though we all sort of understand what causes buffer overflows, they're just sort of not going away, right? And there's plenty of other examples of things that we understand, but that turn out to be sort of hard in practice. This is an example from a great paper out of the University of Florida a couple of years ago about mobile money applications, and this is sort of one example where they were, the company was sort of sending user data and a key to a special encryption server, which was doing the encryption for them and then sending back the encrypted content all over HTTP, oops, right? Turns out like even bad guys have a lot of trouble getting their crypto right. Like if you're writing ransomware, you have kind of one job, right? Which is to get your crypto right. Turns out like that doesn't work. Maybe my favorite sort of recent example came from sort of this new Sony PlayStation device, which is designed to let you play classic games, but only ones that have been sort of properly authorized to play on the device. Well, it turns out that the way that they check for validation of the software that you load on this thing is they actually use a authenticated encryption done symmetrically. And so they shipped every single device with the key for validating the software in a file on the device that they shipped it with. So, you know, which is, I guess, to say that, you know, things that we sort of know, everybody in this room maybe knows how to not do, still happen a whole lot sort of in practice, right? So it can be kind of fun to sort of laugh at these stories, right? It would be nice if people didn't make these mistakes, but I'm here to sort of argue that we need to change our mindset around this a little bit. Instead of asking, you know, what is wrong with our developers, we'd take more of a sort of usable security lens on this thing and say, what can we do to sort of make secure programming easier for people to try to, you know, help avoid some of these kinds of low-hanging fruit mistakes. And of course, there's lots of possible things we can do here, right? Ranging from, you know, better languages and APIs to open sourcing all of our code so that we can check for bugs after the fact and many things in between. But it'd be nice to know sort of how are we going to prioritize among these various kinds of solutions. And even within solutions, how can we sort of optimize them to try to get the most bang for our buck in terms of the actual mistakes that people are making sort of out in the real world. So it would be really nice to understand sort of why these mistakes happen, what the root causes are, so that we can address them. But it turns out this is kind of hard. There's a few different ways we can try to do that, right? So we could do some field studies. We could go visit real organizations that are making software, sort of embed ourselves in the organization and watch what happens and try to understand the way that the mistakes get made. This has lots of great pros, right? You get to really see how this works in the real world. On the other hand, this can be hard to do. Organizations aren't always that thrilled about like researchers wanting to just come in and sort of watch how the sausage gets made. I do have some awesome collaborating partners in that respect who I will shout out, but it can be hard to do, and it can be hard to sort of generalize or systematize from what happens in one organization sort of outwards. We could take some field measurements. So this is just another graph from the National Vulnerability Database, but we could, you know, look at CVEs and look at what types of vulnerabilities exist over various years. We could also do things like, for example, using the Great CryptoLint paper from a few years ago, we could go look at some at code and figure out, you know, what kinds of bugs occur in it naturally, right? So this has also lots of nice positives, right? Maybe these things are in the CVE database are already categorized for you. You know, you can get some idea of what's going on out in the real world. On the other hand, it can be pretty hard to sort of draw conclusions from this data, right? We're comparing drastically different systems to each other. We don't really have any context for what happened in developing this software to understand where bugs came from. And sometimes you can only sort of find the bugs that you're looking for, right? You can't sort of find other ones that you don't sort of already know about. We can also do something that I've done a fair bit of with my collaborators recently with lab studies, right? So these are nice. You bring people in, you have a nice controlled environment, you ask them to do some tasks, you get to watch exactly what goes wrong. So this is great because you have all this control. You can measure like exactly the variable you want to measure. And of course, bringing a programmer in to, you know, work on a task that you give them in 90 minutes or less is exactly like how programming works in real life, and therefore there's no problems whatsoever. No. So, you know, clearly this also has some drawbacks, right? So all of these things are really important and valuable, but they all have these trade-offs. And so something that we've been doing at UMD recently is trying to find another point in this trade-off space. It also has pros and cons, but we think it has some nice, reasonable trade-offs. And that's this build it, break it, fix it contest. So this is a sort of secure development contest that some of my colleagues originally came up with. You can think of it almost as like the weird child of sort of top coder and capture the flag competitions. So our teams come in, they get a couple of weeks to sort of build some software according to a spec. They get lots of points if it's performant, if it goes fast, if it has optional features. Then everybody gets to see everybody else's code and basically hammer on it for a couple of weeks. And when people find bugs in your code, you lose points. You can also get points for finding bugs, but that's sort of a separate category of points. So as people find bugs in your code, you lose points. And then eventually you get to sort of try to fix the bugs that people find in your code to get some of the points back. So, you know, without going too far into detail, the incentive design for this thing is pretty important. You know, we want to make sure that our builders are actually trying really hard both to make it performant and to make it secure, to try to capture some of sort of the trade-offs that you see in real life between people having competing priorities. We also want to make sure that our breakers are sort of looking for security bugs and not just for correctness bugs. We want to make sure that they're attacking a nice breadth of submissions So we don't just want, oh, this particular project is pretty bad, so I'm just going to hammer on this project all day and never look at anything else. And we want to incentivize people to try to find vulnerabilities that nobody else has found in the interest of hopefully getting pretty good coverage over all the programs that we're working on. The paper from CCS in 2016 goes into a lot of detail about how we tried to do that. It works up to a point, not perfectly, but it works reasonably well. And as a result, we end up with something that has more control than some of the field studies I was talking about, although not perfect control, and more realism than lab studies, because these are projects that they can be bigger, they can be harder problems that people work on for a few weeks. Less real than like real world software, but another sort of interesting point in this space. What we've been doing recently is really trying to in-depth look at the mistakes that get made. Having run this contest several times over the past few years and having had about 100 teams participate over the time. So before I talk about the mistakes that can get made, let's talk a little bit about the problems that we asked people to solve. So the first one was the secure log problem. Basically, you had to write a file. You had to write two programs, one to add entries to a log and one to read data out of the log. The setting for this was an art gallery to sort of keep track of all the people coming and going in an art gallery security system. So don't worry too much about like the specifics of the command line, but you have to know the key to be able to write to the log. When you do that, it adds some entries to the log, just like that. Then eventually you can read out and ask sort of, where was Alice today? And it'll say, oh, Alice was in the office today, right? So the threat model for this project is that the bad guy does not get access to the key, but they do get access to the event log as it is stored on disk, right? So as the strawman example, you could just like store your log in plain text with no encryption or encoding or anything else, and then the bad guy's job is to either retrieve information from the log about who was where when, or to edit the log in such a way that the log reading program will give back incorrect information, right? So you can kind of see how that would work. The second one that we have is sort of a secure communications problem modeled after a bank talking to an ATM. So you create a bank, it has this secure auth file, which is basically just sort of the bootstrap secret key for the whole thing. You create an ATM, right? The ATM makes cards. You can do things like create an account for Bob, deposit some money, withdraw some money, and so on. The attacker gets to sort of sit as a man in the middle in between and has the ability to read packets, replay packets, drop packets, things like that, and also potentially gets access to the card file, again, sort of as stored on disk. And then the third problem that we did most recently was sort of a secure data server. So it's basically an access control delegation kind of a problem. You have principals. It's basically a key value store. You can create values. You can delegate the ability to read or write these values to other principals and so on. And in this case, the bad guy just has to try to either read or write some data that he should not have access to according to the delegation. Okay, so what do we do with all of these projects that we have? Well, what we've been doing, and by I mostly mean my very patient and long-suffering grad students, have been examining every project and each identified vulnerability in detail. This includes all the vulnerabilities that were found by other teams in the contest, as well as the grad students themselves look in each program for additional vulnerabilities that were not found or not exploited in the contest. And they're doing a process of rigorous qualitative coding. So we're doing open and axial coding to sort these vulnerabilities into different categories with 2 independent coders. So they've gone through 76 projects and more than 800 total vulnerabilities to try to understand what happened here. And what's kind of nice about this is that there's only 3 sort of projects. So it's a little easier to sort of look at these things holistically than trying to look at like all the possible kinds of software that might get written. And then we're doing some analysis on the resulting categories. So we're measuring things like what is the type of the vulnerability, which I'll get into more what that means in a minute. What is the severity? Whether it's chained, so whether you have to exploit sort of 2 things in a row to actually achieve your objective. Difficulty of finding and exploiting the vulnerability. On a project level, we're coding for things like how modular is the code design, how small did they make their trusted code base, are they doing a good job of commenting the software and things of this nature? So we came up with this sort of approximate hierarchy of vulnerability classes that we're using for this coding, which has sort of 3 main categories. So the first big category is sort of no implementation. So they just failed to sort of implement an important security feature that you need. And this has some subcategories, which I'll sort of talk about in a minute. Then we have misunderstandings. So they tried to implement some kind of security feature, but they just misunderstood what to do with it or how to use it, and it just didn't work. And then we have mistakes, which are more in the class of like, getting a not wrong somewhere or other kinds of sort of, error type details, not conceptual errors, but more implementation errors. Okay. So what did we find out? So far, I will add that everything takes a little longer than you expect. So we're not 100% done with this analysis, but we're getting close. So far, we're finding that non-attempts are more common than mistakes are, and also that misunderstandings are more common than mistakes are. This was sort of surprising to me. I was expecting mistakes to sort of be the overwhelming majority of these problems. Within these categories, we're also finding that implicit is more common than obvious. So what we mean here is we're defining obvious as sort of, it's called out in the spec, right? It's called out in the spec that the content of the log file needs to be secret, and therefore if you don't even try to do any encryption or encoding on it, that's an obvious one. Implicit are sort of not doing a security feature that you need, but it may be less clear that you need it. So if you're not authenticating the log file such that people can sort of overwrite parts of it without being detected, then that's more of an implicit mistake. We're also finding that conceptual errors are more common than bad choices. So bad choices here are sort of, among other things, choosing a weak algorithm or just like making a bad choice about what kind of security primitive to use, as opposed to a conceptual error, making a good choice of a thing to use, but then making a mistake in sort of how to use it. Across the problems, we found that for the secure server, so the key value store, mistakes were most common, and the ATM mistakes were second most common. And this is sort of in order of the complexity of the spec. So the key value store has like a lot of little nitpicky details to try to get right, and the ATM is sort of medium complexity. We also found lots of implicit issues and conceptual errors in the ATM problem, which has sort of a lot of unstated requirements in terms of secure communication across the network. There's lots of things you might not realize you have to do, like protect against replay. And we found lots of bad choices in the secure log problem. I don't really have a handy explanation for why that happened, but we'll look into it some more and see what we can come up with. So let's look at some examples. So in the set of sort of obvious mistakes, we of course saw some people just not do any encryption, or in the case of the key value store, just basically not implementing any access control. There's sort of not a whole lot to learn there, I guess, except that if you don't try to have security, you're not going to have any. On the other hand, the implicit ones, which were more common in this class, we saw a bunch of things like side channels in terms of the length of the messages in the ATM problem, people not having any kind of MAC or any kind of authentication code, not having nonces. In the access control problem, not checking the entire chain of delegation. So, if B delegated it to C, then we're just going to allow C to access it without checking whether B sort of had permission to access it in the first place, right? So kind of missing some of those points there. Where I think this gets the most interesting is where we start getting into some of these misunderstandings. So we have bad choices. So we have weak encryption algorithms, right? We had one team use WEP in 2016. I don't have an explanation for that, but sure. We had people using sort of unkeyed functions to check, essentially an unkeyed hash to check the validity of the log file before they read it back. You can easily see why this is not going to work. And we did have sort of a few cases of people still using stir copy. So sad. Okay. But where this sort of is, these conceptual errors, I think, are much more interesting. So we had a bunch of people do things like only macking a line at a time in the log file. So you can just sort of reorder the lines in the log or just delete one and tamper with it with nobody noticing. We had people doing things like macking the key instead of the actual log data itself. We've had several instances actually of people trying to use TLS. So the most successful version of the ATM program we had used TLS. So use existing protocols, don't build your own. Turns out to actually be good advice that we've sort of been telling people for a long time. But we had a few people try to do this, but without using client authentication. So basically anybody who wanted to set themselves up as an ATM was able to sort of talk to the bank and have transactions go through. So not great. We also saw lots of cases of sort of mistakes using libraries. So only one team actually tried to use a library in the access control problem. There's not a lot of libraries sort of out there to do that. And they found one that sort of did the right thing, except that it was not able to handle loops in the delegation list. And they didn't realize, I guess, that the library couldn't handle the loops, and so that sort of introduced a vulnerability for them. One that I think is really interesting is in the log problem, this one team used something called SQL Cipher, which is designed to basically build in all of the encryption and macking and everything else for you to sort of store some stuff securely in a database. And if you just use it sort of as defaultly set up, it will do the right thing. However, this team actually explicitly went and set a flag to turn off the Mac in using this library. And you're going, why would they do that, right? What on earth would motivate them to do that sort of thing? And as best we can tell from sort of reconstructing their commits and doing some Googling, it appears that they got a weird error message in trying to make this thing work. And in the documentation, it says, this Mac was sort of added as a feature in some version of the SQL Cipher thing. And so it says, if you're using this older version, you can turn off this thing in order to have backwards compatibility, basically. And they got this mysterious error message, couldn't figure out what to do with it, found some post on Stack Overflow or something that said you can turn this off, and that's what they did, right? So we will see this sort of theme come up again. We also saw lots of cases related to randomness. So we saw people using fixed instead of random, hard coding a key, hard coding an IV when it's, and hard coding a password, these kinds of things. So in one case, we actually, let me zoom in on that a little bit, had one instance of a team using this is an IV 456. This comes directly from the documentation and was also copied from the documentation into a Stack Overflow post about using the same thing. So this is a combination of sort of the documentation not telling you that this is not a thing that you should use a static value for, and then Stack Overflow kind of exacerbating the problem. So a couple of years ago, some colleagues and I, actually I think Yasmin spoke about this maybe last year, did sort of a study on problems with Stack Overflow related to security, so it's always nice to see these things that you're doing sort of come back again. So that doesn't work too well. We also saw some instances of people trying to use randomness, but sort of not quite having enough of it. So having a nonce that could overflow, having an IV that just sort of counts up predictably, not in a mode where you're supposed to do that. And having things like a timestamp window too large. So sort of the extreme example of that was checking sort of the timestamp that it was the same day. So as long as you replayed your message to the bank on the same day, then it would go through. But if you waited until tomorrow, it wasn't going to work. There were other instances where the timestamp was smaller, but still sort of not small enough. All these kinds of concept errors. And then we had a bunch of instances of mistakes. So we saw things like a whole bunch of nested conditionals and borking sort of the not on one of them, so that the conditional sort of went the wrong way. We've seen that happen in sort of real world code plenty of times, right? Things like uncaught exceptions or ignored errors. So we had several cases of people very carefully checking the nonce to see that there was a replay and then detecting it and then just nothing happening with the error. So everything just sort of kept on going as though the error had sort of not happened. Other common sorts of things like null pointers and other, memory related issues that you might find. So these are sort of some of the types of things that we found. So in terms of, okay, so these are fun stories, but what can we actually sort of do with this information, or what should we do? Well, this is sort of a drum that I know lots of people have been beating for a while, improving the abstraction levels in our APIs. And I know the community is making a lot of progress in this area, trying to get away from asking the developer to make lots of decisions about what encryption mode to use and things like that, where they can make a lot of mistakes. I think we just have to go like even further in this direction. We have to go to sort of semantic primitives. So not even like, and again, some libraries are sort of going in this direction already, but we need to go even further. What are the sort of semantic classes of things that you might like to have? Well, maybe a secure log is an example of a semantic class you might have, and you would want to just have a library or an API that does that. Or semantic classes of like sending secure messaging that might remind you about things like client-side authentication as well. Also improving documentation, right? So clarifying which parts of the example you are and are not supposed to copy and paste. This will sort of only get you so far because people will just paste it anyway, but it would be nice to at least like include a note in there that that's not a great idea. Mysterious error messages, when you have these mysterious error messages that people don't know how to cope with, this is when they end up at Stack Overflow, and then many more bad things sort of happen from there. And then other kinds of sort of tools and automation. So there's some cool work coming from Sarah Nadi and her colleagues about sort of wizards, right? Like, what are you trying to do? Oh, I'm trying to have secure communications. Do you need to authenticate on the client side? Do you need to authenticate on the server side, right? So sort of walking people step by step through so this goes with this sort of semantic primitives idea. A similar idea coming out of software engineering is sort of API misuse detection, sort of at a semantic level, right? So, which is not to say that we don't still need analysis tools to like find buffer overflows and things, but we need to be able to find some of these kinds of semantic errors. As I mentioned, we have some more analysis coming soon. You'll notice I mentioned that we coded a lot of other kinds of features and then didn't talk about them. So the analysis relating things like modularity, quality of comments, and language used to the types of vulnerabilities that were found is coming soon. Also, we're looking at not just what caused the vulnerabilities to happen, but sort of what made teams more likely to identify the vulnerabilities, more teams more frequently. And we're also hoping that we can get from this some additional insights into how to continue fixing sort of the design of the contest and the incentives to keep pushing this thing a little bit closer toward realism as we go. It's never going to be completely realistic, but trying to get it as close as we can get it. Let's see. And so overall, understanding developer errors and sort of why they arise can be pretty tricky. There's not really any perfect way to do it, but there are a lot of different ways to get sort of different lenses on the problem. We think that the Build It, Break It, Fix It contest is sort of one useful point in this trade-off space for trying to understand how these mistakes happen. We found that a lot of these vulnerabilities came from sort of nuanced security properties. So not as many mistakes, not as many people just ignoring security entirely, at least in the contest environment, but lots of sort of misunderstandings and conceptual errors, lots of non-understanding how authentication works. Speaking as a person who teaches an undergraduate security class, the encryption part, everybody basically understands. The authentication part, nope. That's pretty consistent, so this is sort of maybe not too surprising. And abstractions and documentation matter. So as I mentioned, I guess Yasmin was here last year talking about some of this stuff. It's nice to see that some of the same problems we've been finding in our lab studies about abstraction levels and documentation show up in this kind of study as well, which gives me some hope that these lab studies are, actually reflecting at least some realistic conditions, which is nice. Finally, I have sort of one thing to plug here. My students, we've been doing a lot of work on this sort of security for developers and professionals, and we're putting together essentially a research panel. So this is people who work on either programming or security in some capacity and agree to sort of get an email from us maybe once every 3 months, and really not a ton of them, I promise, asking you if you would like to be part of a study that we're working on. Especially, people who sort of do security stuff in the real world, we would love to have you in our panel. So this is that's the short website for it at ter.ps to get some information to join the panel, or you can come find me afterwards and I will, stand you in front of my laptop and watch you sign up for it. We can do that too. We'd love to have you for that. And that is, and I should thank all of my fabulous collaborators on this work, especially, as I said, the very patient grad students who've been combing through all of this code, and also our funding agencies, NSF and NIST, and this has also been supported by a research award from Google. So thanks a lot. Happy to take questions.
So we do actually have a few minutes for questions. So I think Dan, you were first.
Are you finding any impact of education? Like if you split the group up into people who have taken a crypto class versus people who haven't, are you finding any differences?
So that is one of the coming soon items. We did a little bit of that in the CCS paper. We did some sort of initial high-level analysis, and we didn't immediately find it, but we're gonna try it again. In some of the lab studies that I've done, we've sort of found that having more experience in programming in general didn't help. Having more security experience helped like a very tiny amount.
Wow.
Like it didn't quite reach statistical significance amount. We'll see in this case. It's a little hard to judge with the contest because teams have up to 6 people on them, and it's a little hard to control for on this team, one guy did all the stuff, whereas on that other team, they actually sort of split it up evenly. So it's one of the less great parts of sort of the trade-off in doing that measurement. But yeah.
Very cool work. Thanks.
Thanks.
Hello.
Hi.
Hi. Yes. So where are you classifying errors of this type? Wherein you mentioned one case where if there is an error condition, the code is going via the wrong path, but that could leak some timing information. Why don't we record the error, write junk information into the buffer, and allow the protocol to fall through and eventually fail so that timing information is mitigated? Where is this kind of information classified in your list?
So are you asking about that as an example in terms of how we're deciding the classifications, or about that one specifically?
No, just one example.
Right. So I think there's no perfect classification for this. We came up with a pretty detailed code book. So the qualitative sort of coding standard process for this thing is that you have several independent coders, you come up with a code book, you set sort of boundary conditions, which are sort of well defined. So in the paper that we'll eventually write, they'll sort of be more clearly defined than they were in the talk. And then you go through a bunch of rounds of multiple coders sort of independently grading the same thing and coming to agreement. And it took, in this case, because these categories are pretty hard to nail down, so it took us many rounds to find them, and to reach our agreement. But eventually we hit sort of very high levels of intercoder agreement, which is not to say that there's not some other classification you could also come up with, but this is the one that we sort of landed on.
Okay, thank you. Thanks for the talk.
Yeah.
Hi. I was just wondering if there was a unified testing framework or something that people used, and if there's any correlation between coverage and security bugs.
Right. So in terms of the framework, so the way that this works in the contest is we have an Oracle implementation, which is sort of supposed to be completely correct, and so you sort of submit a test case, and the system runs the offending code and then the Oracle and checks sort of the outputs and sees if they're the same, essentially. It's sometimes a little more complicated than that, but that's sort of the rough idea. So that's kind of how we test them at scale. In terms of what the teams were doing, some of the teams built out pretty serious testing things while they were trying to build their own code. Other teams didn't. So that was sort of one of the categories that we coded for was did they put together test cases, and if so, how many of them? Despite valiant efforts, my grad student didn't quite get that regression running yesterday, so I don't know the answer to that one yet, but I will soon, and hopefully coming to a paper near you, whether or not it helped. In the initial CCS paper, we checked for just at a high level, did they use any automated tools for static or dynamic analysis, and at that level, it didn't make a difference, but it may matter when we're able to sort of look at it in this more granular way.
So two kind of interrelated questions. One, were the specs written so as to sort of limit error in a defensive way? And also more generally, have you looked at the relationship between specs and the output?
Yeah, so the specs were written to be as clear as we could make them. I certainly think they were probably far from perfect, especially the access control problem. That one was really complicated, and I think if we were going to do that one again, we would probably sort of revisit the way the spec was written a little bit. So to take one example in that one, for that problem, we tried to support availability errors. So basically, if you could create a situation where the person who's authorized to access the data can't get to it, that was graded as a security error. But it turns out that it was possible to sort of upgrade some very basic, like parsing the input errors into availability errors and count them more than we originally wanted to. So it kind of messed up the incentives of that version of the contest a little bit. So yeah, I didn't go into it in this talk, but like trying to design the problems and then put the specs together for the problems is a huge amount of effort and makes a big difference in how well the results turn out.
As someone who teaches cryptography from time to time,
yes.
I sometimes feel like I'm fighting a losing battle with Stack Overflow or Stack Exchange. Do you have any advice for me as an educator?
Yeah, so I think we're probably all fighting that battle, but I think it helps a little bit to sort of point out that these things happen, right? Like maybe especially some of our students, maybe it hasn't occurred to them that like, that bad things can happen if they sort of follow the instructions that are in there. But I think really the real answer is sort of systemically we have to make the documentation and the APIs themselves better, because you're not going to stop people from Googling when they run into a hard problem, right? And so what you need is for like the error messages to be more understandable, and you need things like when somebody Googles for a specific weird error message, you need to get like the official documentation back or something from a more authoritative source instead of ending up, sort of at Stack Overflow instead, right? So that's, in the long term, that's the only thing that's going to fix it, I think. So.
Wait, Chris, is your question quick?
Yeah.
Okay.
Thank you. That was cool. What group of people are you after for this study, and how do you incentivize that group to actually participate?
For the contest?
Yeah.
Right. So the first couple of rounds we did in two different ways. So one of my colleagues, Mike Hicks at Maryland, was teaching a Coursera class, and the sort of capstone of a security sequence in Coursera was to basically participate in this contest. And so that was a nice source of participants. It had the nice property of like most of those people are sort of working programmers and not like undergraduates. We love them, but they're maybe not always the best possible test case for this kind of thing. Although we do actually run this in our undergrad security class a lot, and so we haven't analyzed that data, but we could look at that as well. We also sort of did an open contest that we tried to advertise to sort of everybody we could think of, but we didn't have a lot of great luck in recruiting for that. So we're sort of still revisiting if we're going to do this again, where we're going to get people from. So we've maybe been talking to like some companies about if they would like to have some of their developers participate as sort of a fun exercise. Yeah, we're kicking around ways to find more people, because that's definitely a weakness of the sort of another point in sort of the trade-off space, I guess.
Thanks.
Nope, sorry, we're out of time. I'll have to ask you to take that in the hallway. I'd like us to show our appreciation to Michelle and Bailey and Chelsea and Josh for an excellent session. And we'll see you all out there in a few minutes for drinks.